built and experimented with 1/4 of height scale and 1/1000th of the power scale model of AHWR for flow instability studies, full-scale AHWR fuel bundle for CHF studies. He is founder secretary of Steering of Committee Indian Nuclear Society and current president of the Indian section of the American Nuclear Society. He supervised to completion 102 MTech and 18 PhD dissertation. I welcome you, sir, and invite you to please deliver your talk.
Over to you, sir.
Hello. Good afternoon, all of you. Hey, how much is the time? 25 minutes? 20 minutes? 30 minutes. Okay. So it's 2:31. So I'm allowed till 3. So I'll keep a watch. So I have a dynamic clock there. So it should probably keep track of it. Okay, my name is Kannan Iyer. I used to serve IIT Bombay. I retired in 2020 and joined, yeah, it's too much of noise or what? Achha, I have to be here. These days, of course, you have to be more for a camera than for what, maybe for the audience, I guess. But that's part of the game. All right. So anyway, I think I have done it as a mathematical presentation. So it's slightly different from others. But at the same time, I will keep in mind that the students have to be taught physics. Or, of course, Professor Balaji was saying physics need not be done anymore because the governing equations are also not required. Everything can be done. The machine can learn on its own. So it's something I don't understand still. I thought I will learn from his talk, but still I have to learn some more. I think some books were suggested, maybe I'll go there. Having said that, so, okay, from here, anyway, I think I have written it, so I should be able to understand what. Let me start. So the organization, the way I have organized this, I will introduce why I did what I did. And it will be very funny that quite often, when you are in a university, and here is an example where I was funded by DRDO in the beginning. And it so happened that the DRDO project itself got wound up, and they told you quickly wind up because we don't have time. Because the project, which was a bigger project or whatever, so that itself is gone. So therefore, we can't support more than 2 years at the moment. So therefore, now I had to run here and there and figured out that on a similar work. So I got some support from ANSYS Fluent. And eventually, therefore, the PhD support is always very important, and particularly when somebody is an externally supported student, and suddenly they say the project is not there, so you can go through here. So I can understand maybe Amity may be going through something, but most of the government universities like IITs, we don't. But IITs, we have a couple of types. One is sponsored PhD students and the regular PhD. So the sponsored PhD has always to be sponsored. So I just somehow managed anyway. So this whole story is about the work, how we started and how we ended. Okay, then I will tell you the objectives of what we were doing and how we were motivated and what were the eventual objectives. Describe the problem and look at the treatment of bubble growth. For example, what you will find is that in cavitation, eventually the evaporation and condensation is important. It will become clear why. And we use there are many empirical correlations people have used. We chose one route and eventually came out with some answer. So I'll tell you what we did. And of course, any model which you hypothesize has to be verified by appropriate application, whether the application agrees with what you have proposed. And if it agrees, then you got a theory, and the guy gets a PhD. If not, he struggles further, and finally he gets something. So that's part of the game. All right. Eventually, I'll present the conclusion. The pictures are pretty bad here because I'm seeing at an angle. I hope you are able to see. Basically, what you see here is a projectile, which is, suppose you fire underwater. So when you fire a projectile underwater, then what it does is it's going at a very high speed and it's also moving. So the velocities accelerate near the nose. So the local pressure falls below the saturated vapor pressure. And as a consequence, it cavitates. So that means it evaporates. So, of course, lot of evaporation is going on, the projectile is moving. So, if I say that normally what you do in fluid mechanics, if the projectile is moving and you want to study it, you immobilize the projectile and move the fluid relatively in the opposite direction and see what happens. So, essentially what will happen near the nose, etc., there will be a lot of evaporation. And then fluid is also moving, it's carrying, and near the tail, what will happen is the pressures are building up because the velocities have decreased, and therefore the ambient pressure goes above the vapor pressure, so it starts condensing, and eventually the entire bubbles coalesce, completely is gone. So therefore you see an envelope. What you really see in this, it's actually a drag reduction technique. That means, remember, if you are firing a bullet, and it is going with some momentum, it will slow down because there is a drag. And therefore, if you don't want it to go fast, number one, and number two, long distance, then you need to reduce the drag. So one of the ways of reducing the drag is to change the fluid in front of it itself. Okay, so therefore, this supercavitation, normally we think cavitation is bad. It affects materials, so it's not good. Here is a case where cavitation is good, because it reduces the drag. Okay, so now, is it true? And here is an experimental picture. This is a Russian work. And I don't know whether you are able to see the projectile completely covered with vapor. Okay, so therefore, this is a Russian work. So, and to explain to you, that's what I said, that there is a acceleration of the fluid near the nose, pressures fall, and so cavity forms, and farther down the velocities decrease and the cavity eventually collapses. Okay, how did we begin? So IIT Bombay had a so-called a memorandum of understanding with Navy, so that some Navy officers are posted to IIT to do MTech. So there were two Navy officers, Grewal and Anurag. That is Anurag Sood, that is. So I'll call him Sood. And they, particularly Grewal, said that we want to work on supercavitation. I had no idea what it is. So I started looking at, and then we said, okay, let us start working on it. So we had ANSYS Fluent license, and ANSYS Fluent license has a cavitation model built in it. So therefore we said, okay, let us start on it and see what we can get. So Grewal started in 2007. He sorted out complete numerical methodology, and I'll show you some of his results. So eventually what happened was, numerically we sorted it out. We benchmarked it and then did parametric studies the way normally any MTech work does. Everything was assumed steady, everything was great. Then when the next student came, the next lieutenant commander, he wanted to continue. So I told him, no, numerical is over. I said, let us see if we can build an experiment. So we actually built an experiment with a very little resource we had, maybe about 1.5 lakhs or whatever I had in my professional development fund. So because the Navy things, projects has to be finished in 1 year. So I can't write a project, it will come, God only knows. So I designed some, and one good thing about this Navy people is they go after it. So therefore it gets done. Okay, so he built an experimental. Oops, sorry. All right, so this is Grewal's work. That means first we benchmarked it, and at that time we had a funny idea that the front of it will be a cone. Okay, because we did go to DRDO, but we did not get much information from them. So anyway, as I told you, the time is very short for us, we have to move. So whatever wisdom we had, we thought that the overall thing will be a cylinder with a cone as a basic geometry. So for a given cylinder diameter, various cone angles were taken to find out what is the cavity, what is the coefficient of discharge, etc. And some correlations were developed, and he finished his work. So you can see that if you change the geometry, the cavity length appropriately changes, etc. So only thing I want you to know is, yes, depending on the shape, the cavity changes, the coefficient of drag changes. Okay. And I'm going to stop from there because my concentration will be on the basics as we go along. Then we built the experiment that is, Sood built this. What you see is an air gun in front of a big square box so that we can fire our projectiles. So we got small projectiles machined in our workshop. Oops, it jumps too sometimes. Oops, all right. All right. So first we conducted a trial on simple air. So it almost went with about, I think, 140 meters per second. So whatever we thermodynamically we designed, it was working. And then we shot the bullets. And when we shot, we got a very big surprise. Yes, the bubble came, but the bullet was unstable. We fired it straight, but it was swerving. It was going in all kinds of directions depending on how you fire. How you fire means it is not repeatable, it is statistically varying. So then it became a major problem as to what's going on. Okay, so out of one day, out of frustration, I told Sood, yaar ulta laga ke chalao yaar, let us just fire it from a bigger, just put it upside down, because we thought that at the point, there is some, what do you call it, depending on whatever angle changes or whatever, let's fire it from the rear. So we fired the bullet from the rear. So we were very surprised. It went straight. And typically, basically what we found, that why is this happening? And then we understood that when we did the numerical one, all the force is, all the drag is just at the front. Okay, the whole rear, because it's all covered with vapor, so therefore it is like a point force. It's just like a pencil, for example, is trying to stand on its point. So if you want to make it stable, it will always fall. But on the other hand, you put with some base, then it works. So that means you should not have a sharp, but you should have what is called a blunt projectile. That means in the front, there has to be a cavitator of certain dimension. And when we worked at Russian work, they always have been talking about a disc, and they don't talk of anything else. So we were wondering, why is it they are always talking about a disc? And that we understood subsequently why they talk about a disc. I'll tell you in a moment. So after we figured out that there are some issues, so I asked him that, no, because these are projectile where I have no control at the moment. So therefore we asked him to do different blunt projectiles, some experiments, and then we did numerical simulation for blunt projectile. And there we got the picture that here on the top you see a blunt projectile of a size of the front. Blunt projectile is nothing but a cylinder with a cone but a frustum, you have cut a little bit. And you see on the second one below is simply a disc of the same diameter. And the fluid is traveling with the same velocity. What you see is the cavity is almost identical. So what that tells is that the disc is the controlling fellow, because all the cavitation is happening around that point at near the front, and everything else is just developing, condensing, and so on. So therefore, interestingly, if you are going to design a torpedo or whatever, so you just get the results of a disc and ensure, and once you know, if I can characterize the geometry, which we have done, what will be the diameter, what will be the length, etc., then so long as the body is within the cavity, you don't have to do anything. So that's the design. That is, do a disc, calculate how much drag it will have, and then simply design a geometry inside that geometry, what you get, then that is enough as far as the projectile is concerned. This is the conclusion which we eventually came up with. And therefore, these were 2 free projects we had, because we have free students. And now we thought that we went and talked to NSTL and showed some of these results. They were very happy. And then I told them that the main problem is we want to study is on stability of this projectile, how to stabilize them. So there are 3 ways of stabilizing from the, whatever you see from the literature. One is fin stabilization. That means you have some fins, so that will try to provide resistance for it. And there is spin stabilization, just like a bullet, you spin it so that the gyroscopic action stabilizes it. And there was a third thing, what was called the cavity stabilization, that is the tail slapping. So what is tail slapping? And that looked very interesting to us. So since we wanted to study something basic, so we wrote a proposal for this tail slapping stabilization. Okay, so what you see is, I have shown it looks like a little odd shape, but I'll tell you why we got this odd shape. But the idea is you have a front and therefore a bubble is generated. That much is clear. So now the tail slapping is nothing but it is going to be unstable, let's say. So it will swerve. So as it is swerving, then it will hit the water, and when it hits the water, it will get a reaction. So it swerves back. So therefore, it will be like kind of a fish moving. It will be swerving like this. So it travels in a straight line, but it just moves a small amount of motions. It will be generated continuously, and therefore we thought. Therefore, now it becomes a fluid structure interaction problem. So it is just not a fluid problem, it's a fluid structure interaction, so it attracted us. So they gave us a 2-year contract, and as I told you, within a year and a half, they told quickly finish it because of whatever. So we had done the tail slapping, but they were supposed to do the experiments, but eventually nothing was done. So at that time, so this introduction was probably to introduce not only cavitation, tell a little bit about supercavitation so that you learn something about it, and eventually it not naturally leads to probably what we did. So therefore, what we did, in 2018, I had convinced ANSYS Fluent to give us a contract, and I managed to get a contract to basically their cavitation model. They have a standard model called Schnell and Sawyer model. So that was working many places, but in cryogenic cavitation, that is cavitation which occurs at when the fluid temperature is close to its saturation, it does not work. So there are problems under what is called cryogenic cavitation, because those would be important for space application and other things. So so of course I told them that they don't have to give anything else other than 3-year PhD's fellowship, so we could manage it. So we started the work. So this time our aim was to understand the cavitation model per se. And one good thing working with Fluent, they have already done standard cases. That means they have already got several things done. So here it works, here it does not work. So therefore our job was to get a thing and just start verifying. So the project became easier that way. But then there was a lot of issues because we had to manage it with Fluent. And we have to generate, that means I don't know how many of you use ANSYS Fluent, you can generate what is called a user-defined function. So you can write your own routines and embed it in Fluent. So many of the user-defined functions we had to do, but we managed it. Let's see what we did. So basic idea was you have to understand the governing equations. There are some closure relations. I'll tell you what those closure relations are. Our contribution is fundamentally the closure relation, because the mixture model is already there. So we just use the mixture model. So mixture model means you treat the liquid and vapor as a mixture and you run a model. Those who are working in CFD, they will know. And those who don't, if they have any issues, my email ID is in the first slide. You can always write to me and I will always be able to help you out in whichever way. Anyway, so it just jumped one, I don't have to go back, but I've just written the governing equations, don't bother. These are standard equations, which is conservation of mass, momentum, and energy. And if you are having turbulent flows, you have to have what are called turbulent closure equations, which are normally, many of you who is doing CFD will know that you have a K epsilon or whatever, which is very popular. So K epsilon model equations are also written. And we also have to have an energy equation because there is evaporation going on. So therefore, there is an energy equation also needs to be written. So there are people who do not use energy equation, and there are people who use energy equation. So that means, I think that may be confusing at the moment. If somebody wants to know more, we will see. But we have used both with energy and without energy. Okay, I basically have listed all the equations. One thing what I want you to tell is that I don't know if you have heard of anybody working in computational fluid dynamics here? Few, all right. So there is something called a volume of fluid method, right? So therefore, when I want to do in two-phase, I have to have a volume of fluid. That is what is my alpha equation. My alpha is nothing but the fraction of volume of vapor in the whole system. So that is what we call this alpha equation. It is present as the last equation in the previous one. So remember, when you are doing a balance of vapor, you need to know the rate of change of mass in a control volume will depend upon also the source and sink term. If there is evaporation, there is a source added. If there is a sink term, there is a sinking of that vapor, or it's dying, condensation. So the two closure relations are what is the evaporation rate and what is the condensation rate. Remember, if the local pressure in the cell is below the saturated vapor pressure, there will be a source. If the cell pressure is above the saturated vapor pressure, it will condense. So therefore, depending on whether the local pressure is above saturated vapor pressure or below saturated vapor pressure, either the evaporation term or the condensation term will trigger. Okay, so it already has an equation. The kind of equation they have, I have already written on the top. So basically what it is there is some physics, but what happens is they basically have to understand the so-called radius. Okay, what's the model? The model normally here is there are a lot of bubbles which are naturally present in the system. They are called embryos. Embryos are already there. The number density is like 10 to the 9. So now what happens when they come to a pressure lower, these embryos grow. And when they go farther away, these embryos die. Okay, this is roughly the whole idea. So once I know the number density, I know the radius of each of the bubble, then I can calculate how many number per unit volume is there, I can calculate the void fractions. Let me again reiterate. We assume bubble numbers are small bubbles are all floating. Where the pressure is low, they will bloat. And where the pressure is high, they will just go away. Okay, this is the rough model. So therefore, now what they have done is it depends on the pressure and the radius. Typically, the rate of change of radius is the velocity. And the velocity actually comes from what if you take a momentum equation, then if you throw away viscous term, if you throw away surface tension term, then you are more or less left only with the convective term and the pressure term. And therefore, they have come up with they use what is called a Rayleigh's model. I don't know if anybody who works in bubble growth, he will understand what's a Rayleigh's model. Idea is, if I have a bubble which is at a higher pressure, it will try to expand. So it will push all the liquid. And in the beginning, if I assume that the pressure change is very little, then in such a case, only the transient term and the pressure term is used, everything else is thrown away. And when you write that, then it becomes, I have written the equation which is dr dt is equal to square root of 2 by 3 into delta p. Basically, the delta p drives the bubble, right? That's the idea. So, but this is valid only for very small bubble when it is just about to grow. See, there are what are called inertial growth, inertial control growth. That means the pressure is high, it is able to push it. But when it expands, the temperature falls of the fluid inside. So when the temperature falls, the interface is cooler. Because the interface is cooler and the fluid is hotter, it will drive heat into the system, and that heat can evaporate the fluid. Okay, so therefore heat transfer is any heat transfer which is due to the temperature low of the interface, and the heat is simply coming out from there. Okay, so therefore that is not important when the pressure is high and it is able to push. But on the other hand, when it is pressure difference is small and it is very close to saturation temperature, then inertia is not controlling, it is the heat transfer that starts controlling. That is called the heat transfer control. So the bottom line is, when you are in inertial control, you can use Rayleigh's equation. When you are in heat transfer control, you just cannot use Rayleigh's equation. But these guys just put Rayleigh's equation, some coefficient, it does not work somewhere, so you modify the coefficient, tune it and run it and so on. That's what they were doing. So therefore it was very clear to us that we have to work on heat transfer control growth. So we started working on heat transfer control growth. And I have listed some equations. At the moment you don't have to bother. Remember, what I have to do is the bubble which is growing, and it is pushing the liquid. And remember, liquid is considered incompressible. So once it is incompressible, for example, if I have a Cartesian geometry, then liquid will travel with the same velocity everywhere because it's incompressible. That if end of the pipe, if the velocity is p in a constant area pipe, velocity is u, it will be u at the end also because the area is constant. But when you have a sphere, it will go as 1 over r square. Right? It's basically 4 pi r square into velocity. That should be the flow. The same flow it will push everywhere. Right? So therefore, I know the velocity distribution. And remember, it is incompressible. So d rho dt term does not occur in the continuity. So therefore, it is a quasi-steady. If I increase the velocity, everywhere the velocity will increase with 1 over r square. I know the so-called velocity profile. Since I know the velocity profile, I do not, what I have to do is only solve the integral momentum equation. Because I only need to know one velocity, which is the bubble velocity. Every other velocity I will find out in the liquid. So there is no problem. So that is one thing probably you want to, one physics. And rest is what we have done in a Lagrangian framework. So therefore the shells are moving. So convection can be ignored. So it is only we have to worry about that rate of change of energy is equal to the, energy conducted in. Okay, anybody who wants detail, I will always present it to you. But at least what we are trying to say, same bubble growth plus some conduction equation solved for my liquid, because the interface temperature is lower and the bulk temperature is higher. So it is like a semi-infinite plate type if you want. People have done analytically, we have done numerically to improve the accuracy. Okay, so basically what we have done, I have put some ODEs. The ODEs we are simply solving by Euler implicit method. And the partial differential equation, which is only required for the conduction analysis in the liquid, we solve it using a control volume methodology. And so typically we iteratively solve for every time step. And so therefore first is we want to validate it. So we have taken a data of Scriven, how particularly in heat transfer domain. So how the, the saturated model has been validated by Scriven's data. And Scriven's analytical solution, let me call it, sorry. And then we have taken two cases. One is the inertial bubble growth. Of course, this we use always. See, whenever people use bubble growth in two-phase, they assume bubble to be saturated. That means because the liquid and vapor are in contact with each other, the bubble is assumed to be saturated all the time. Okay, so therefore, if I use a saturated model, what I see is when it is inertial control, see, there is something called a Jacob number, which turns out to be a non-dimensional number. I think it is shown to be 2,740 or something. It is in inertial control. When you are about 10, 15, then you are in heat transfer control. So for inertial control, multiple models are shown. They are similar, not much difference. But when you do heat transfer control, not only people's results were not coming, and you tell me, 5 minutes? Okay, so I'll close it in 5 minutes. Okay, so therefore, what we did, not only people's model did not work, even our model itself, saturated model, did not work. So therefore, it became clear that we have to use the energy equation also for the bubble. So we also use the energy equation for the bubble. Sorry. Okay, so in the previous slide, we have used the energy equation and the results agreed pretty nicely. Once it agreed, then we did, oops. Okay, so what you saw that it agreed. Now we did a parametric study. And when you do a parametric study, it is very interesting that in the very initial time, they are all different, but eventually they asymptotically come to one curve. So, and those initial things are for very short time. So we postulated that we have to only worry about the enveloping curve. So therefore, what we did, we converted into a non-dimensional numbers and R plus and T. This is again there in the literature, and we could collapse it into one curve properly. And we had a nice curve, which is independent of the Jacob number. And therefore, we had good hope that it can be done for a CFD, because even local changes, something will not matter. So we did it, and we compared first with all this correlation which we fitted, we compared with all the bubble growth data. It agreed fairly well. And therefore, we were very confident that this expression will be good. So then we went into applications. So number one is we have taken what is called cryogenic cavitation, where everything was a problem. So basically what you will find here, the standard model is deviating, I think, with a red line or whatever. And you find that we have two models. At the moment, don't worry about it. But both of them were doing fairly okay. That means you need to do the energy equations, and our overall, instead of having a one single expression like they have and coefficients, we generated our fit, and that worked pretty well. And similarly, for example, there is another case where it is a hemispherical body projectile, and there also the results were fairly okay with respect to. And if I go to, oops. Okay, I have a third example in a capillary tube, and there also it worked. So therefore, after I have only showed 3 of the examples here. We have actually done about 8 problems. of, because the fluent only then it will get qualified. And it basically found that in all cases it was fairly okay, so they accepted. And so therefore overall what I say is the new collapse curves which you have come up with, I think that, the new correlation which we have come up with is doing a very decent job for all cases of cavitation, so it should be reasonably okay. So therefore, and only thing what I have not told here is it is a time dependent phenomena. How do we convert it? Because otherwise you have to track every bubble. So how did we manage without tracking it? So we have done a transformation. I think those who are really interested, because the time is running out, so anybody who wants it, they can, I can tell them. So therefore we have done a transformation, and therefore it works very nicely. So we got a patent along with Fluent, because I told Fluent that you take care of the plate and we are not interested. So we got a patent for this new transformation kind of a technique. And finally, we have some journal paper and some conference papers. I think I'll stop here. If there are any questions, I'll take.
Yeah. Okay, so what I'm understanding is that you added a source term to the energy equation.
Yeah, almost everybody does.
Right, yeah. So what I'm...
Yeah, go ahead.
So what I'm working in right now is I'm using the VOF method to simulate flow in pulsating heat pipes and thermosiphons.
Fine.
Right? Over there, they also do something similar. The evaporation...
Navier-Stokes, or it's a one-dimensional model?
No, that's Navier-Stokes.
Okay.
Yeah.
Okay.
So over there as well, the evaporation and condensation is occurring, but that's occurring primarily due to the heat added to the heat pipe.
Right.
Right? So they also add a source term using a UDF.
Right.
And it had a very what they use is called a Lee model. It's
Fine.
Yeah. Anyway, so the point is it had a very similar structure as to the model that you were showing that was already present in Fluent.
Okay.
Right? And what I was what I want to ask you is it also has a coefficient, the CE and CR coefficients.
Yeah.
And it seems to be that the convergence is very sensitive to that coefficient. And that's what I'm trying to,
See, that's the whole problem. That C business is, you don't even know what C to use.
Exactly.
They have done something here, something there. So our problem completely gets away. There are no C's at all. So however, you may ask, is there no empiricism at all? No, actually there is the bubble number density. How many bubbles are there per unit fluid volume? That we have obtained from here and there. We have not correlated yet. It is still the work in progress. More or less in the next 10-15 days we will wind up. Okay, so I can share with you whatever it is. So you are welcome to write to me and we can discuss much more detail over Zoom meetings or whatever.
Thank you so much.
Welcome. So the purpose of conferences are these, to connect some people. Well, 2-3 guys are connected, then paisa vasool, right?
Yeah.
Any other questions? All right. So, thank you, sir, for your invaluable insights in the use of CFD modeling for a cavitation flow. I now request the session chair, Dr. Behani Ray, to felicitate Dr. Iyer with the token of gratitude, memento. Give a huge round of applause as we present our moment of gratitude to Dr. Iyer. Thank you, sir, and thank you, ma'am, for your benign presence in this keynote talk. This marks the end of this keynote session. Parallel keynote sessions will now begin in their respective venues. Any delegate having their keynotes in their venues can report to the same. I now hand over this session to Apurv and Harsh. They will continue from here. Thank you.
Good afternoon, ladies and gentlemen. I, Harsh Gupta from BTech 4 Mechanical Engineering 4th year. Welcome you all to this gathering. I would like to invite Dr. Pramod Kumar, IISc Bangalore, our session chair, Dr. Sachin Singh Gautam, and session coordinator, Dr. Pallab Gupta, on the dais. Professor Pramod Kumar. Yeah. Good afternoon. First of all, I would like to introduce our keynote speaker, Professor Dr. Pramod Kumar, Associate Professor, Department of Mechanical Engineering, Indian Institute of Science, Bangalore, Karnataka. His title of talk is Novel Supercritical Carbon Dioxide Cycle for a Waste Recovery Application. Dr. Pramod Kumar received the Master's and the PhD degree in Mechanical Engineering from the Indian Institute of Sciences, Bangalore, India in 2001 and 2008, respectively. He is presently Associate Professor of Mechanical Engineering at IISc prior to joining IISc as a faculty member. He worked as a research engineer at the Georgia Institute of Technology, Atlanta, GA, USA. He works broadly in the area of thermal systems. His research interests include the development of supercritical CO2 or carbon dioxide power generation technology, PCM coupled heat pipe or for spacecraft thermal control, and high-speed electrical motors for SCO2 turbo generators. Dr. Kumar is elected Fellow of the Indian National Academy of Engineering. I would like to also introduce session chair Dr. Sachin Singh Gautam, Department of Engineering, Mechanical Engineering, Indian Institute of Technology, Guwahati. I would like to call Dr. Pallab Gupta to felicitate our chief guest with the sapling. Now I would like to call our keynote speaker, Dr. Pramod Kumar. Thank you, sir.
Very good afternoon to all of you. Yeah, so I'm going to present largely the work that have been involved in the last 10 years. And this is the work that we started at IISc, and probably the only place in India where there's work happening on supercritical based carbon dioxide power plant technology development. So this, considering the large cross-section of audience, so I'll go to basically talk primarily on what the research challenges are, and then what it takes to really develop a product, and what we have faced in the last 10 years on trying to develop this technology. So there's a video. So I'd like to play that video. Okay, so if you look at supercritical carbon dioxide, sorry, I don't have a pointer, but so if you see the red dot out there, so that's the critical point of carbon dioxide. So anything, if you operate a cycle completely above the dome, then it operates in the supercritical phase. So in the supercritical phase, you don't really have any phase change. So you don't see the issues what Professor Kannan Iyer mentioned about cavitation and other things, but and then you have very close to, you'll have single phase heat transfer. This is what is suggested in the literature, but I don't have a first-hand experience on this. And then what we really have felt is that the properties in the supercritical phase, the fluid actually behaves like a gas, but it has the properties of a fluid. So that means it has a kinematic viscosity and density equivalent to that of a fluid, but it fills the entire container as what a gas would do. So what it means is that you have now an extremely dense fluid in gaseous form that is trying to expand. So you can shrink the size of turbomachinery to a significantly smaller footprint compared to what you would see in a normal superheated carbon dioxide, superheated steam, or just an air Brayton cycle. So typical steam turbines will operate very close to the saturation curve, so you have to ensure that you don't have wetting. Normally what you would do is you would reduce the condenser pressure to less than atmospheric pressure, so your dryness fraction is maintained to about 0.7. You don't have all those ill effects when you use a supercritical Brayton cycle. So the novelty of the working fluid is, again I'll show you on some TS and PH diagrams, that the best part that what I've seen, I teach thermodynamics at IISc, so the best thing that I've seen, and that is really the novel part of SCO2, is when you expand carbon dioxide isentropically in the supercritical phase, there is hardly any drop in temperature. So from 535 degrees Celsius at about, let's say 143 bar, you isentropically expand it to about 90 or 95 bar. Then the drop in temperature is just about 30 to 40 degrees Celsius. So that means that you can recover a significant amount of heat at the exhaust of the turbine, and this theoretically is supposed to make the cycle extremely efficient. So we all know what you've studied in heat transfer and thermodynamics is Stirling cycle, if it is 100% recuperation is there, it has the efficiency similar to that of a Carnot cycle. So recuperation certainly does help in improving the efficiency, but there are a lot of flip sides to how much you can recover and how quickly you can recover that heat. So those are some of the things that we'll address once we start, when we try to realize the cycle. So this statement, I intentionally put it as, in a different color. So the world is sold to the fact that, you have very high thermodynamic efficiency in SCO2 cycles. But our first-hand experience has shown that theoretically, yes, but practically the efficiencies are lower than that of steam. But now the question is, why do we need to do research on SCO2? So SCO2 cycles have certainly an advantage. You can start it similar to an automotive engine, that you just turn on the battery and then crank the engine and it starts producing power. So SCO2 cycles have very low latency. They have quick start and stop, so you can have many number of start and stop cycles within a day, so you can recover a large amount of throughput. The biggest advantage of SCO2, why the work should really be pursued, is that you have higher heat rejection temperatures that makes the cycle completely waterless. Now we know that water is a precious commodity, and SCO2 can certainly has a potential to replace water. So in my own perception on working for last 10 years, what I feel is a working fluid has to be cheap, and water is no longer cheap. So if you consider water is available in abundance, and then it's available in the liquid form, but purification of water is a very expensive affair. In the morning, I think there was one slide which shows that 1 liter of water just in your house will cost you about 1 rupee per liter. But purification of water, what you need is significantly expensive, especially the boiler grade water. So in that sense, SCO2 certainly fits the bill that it can now be completely waterless. The cost of the working fluid is going to be significantly lower. Okay, so another advantage of SCO2, this is our own understanding in the last 10 years, is that this is probably the only fluid that can work in a single cycle with both power generation and refrigeration. So theoretically, any thermodynamic fluid can actually can work in the reverse Brayton cycle as a refrigerant, even water. But something that can be realized in reality is probably only supercritical carbon dioxide. So you can combine these two cycles, and you can run it through a single loop to generate both power generation and refrigeration within the same loop without having to duplicate many of the equipment. So there is actually, if you Google and see, there are a lot of SCO2 symposiums, and then there is also in gas turbine conferences a separate track on SCO2 power generation. And what amuses me is that we all feel thermodynamics is trivial, but then SCO2 power cycle development is still the state-of-the-art research. There is a lot of companies that still invest heavily on the power cycle development. And then one would wonder that why is it that SCO2 cycles are still being researched? Thermodynamic sense. Okay, you should have transited in last 30, 40 years of research, you should have transited to actually making components and realizing. But SCO2 thermodynamic cycles are still a part of mainstream research, and I will tell you quickly in a couple of slides that why it is so. Okay, so many times people ask, what is the difference between the steam Rankine cycle and the supercritical Brayton cycle? So, supercritical Brayton cycle operates in single phase. So you see to the right, on the bottom right corner, you see that there is absolutely no phase change. So it works completely in the supercritical regime. So it enables us to replace the pump with a compressor. But whereas in the steam Rankine cycle, you need to have a pump. But then the pump work is minuscule compared to the amount of power the turbine develops. But in this case, close to about 40% of the work that is done by that's generated by the turbine is consumed by the compressor. So SCO2 cycles have to be tailored. It has to be very specifically and carefully designed. And another thing is, in the subconscious mind, you think that even steam Rankine cycle is a closed cycle. But in principle, it is not a closed cycle. SCO2 cycle is probably the only cycle that runs in the closed cycle form, that you don't let the fluid to go out. All other cycles are inherently open cycles, be it a gas turbine or a Brayton or a steam Rankine cycle, where you have infinite time for heat rejection to take place. So in an SCO2 cycle, it's very difficult. You have to actually, all these processes are limited by time frames that you have, so the cycle design is extremely critical, and including the choice of components. So over the last 10 years, what I've realized is it's not the turbo machinery, what the literature says is the most critical and difficult part. It's actually the heat exchangers in an SCO2 cycle that is the biggest bottleneck and the impediment into realization of this technology. So let's look at the simple recuperated cycle. Simple recuperated cycle means that you have only one stage of recuperation. So I will base all my analysis to give you a little bit flavor on SCO2 power cycles by just looking as a case study example of a simple recuperated cycle. Okay. So it has three heat exchangers, a gas cooler, a recuperator, and a receiver where it actually takes heat. So now if you look at why SCO2 cycles are so difficult is, on the right hand side, actually if you see, the amount of enthalpy that is added over a large range of temperature is very small. So when you actually build a control system or you want to actually test it, you need some amount of information that the system gives. So if you want a small change, you add some small amount of temperature, you should at least see that what it is doing. So it's like, if you heat water and then you want to convert to steam, and suppose somebody says in the middle of, when the volume dryness fraction is about 50%, if somebody asks you how much heat have you added, you don't really have an answer. You can now, because you are not able to measure what the temperature rise is, depending on the quantum of heat that is added. So it is always a derived property. So similar is the problem with the CO2 cycles. You really don't know how much of quantum of heat that you're adding, because heat addition is over a range of temperatures, the enthalpy change is so small. So it becomes quite difficult to control this process of heat addition. So why is it important for India? So my main take on why it is important for India is because the whole world has not developed it. So we are all on the same page. If we develop it, we are going to be the first. Okay. So, and India also, so I think it has the potential that we have started late, but it doesn't mean that we are going to end up also running late. If we do the work diligently, we might actually be one of the world leaders in SCO2 technology. So it is important for India to invest in this technology and realize it. And more importantly, India now is going to be, our vision is to have more of manufacturing processes that are going to be, homegrown manufacturing processes. So waste heat from any manufacturing process is a very critical part of energy efficiency of the process itself. So SCO2 cycles perfectly fit this bill. So investing in an SCO2 cycle, which is completely waterless, makes economic sense for us to also get into this development. So quickly coming to the research issues. So we all are, intrigued by the numbers of Carnot efficiency or the thermodynamic efficiency of a cycle. But where it will actually really baffle you is, just look at this case 1, where we have 10 megawatts of heat that is available, and then you generate about 2 megawatts of net work. So your thermodynamic efficiency of the cycle is going to be about 40% is the Carnot efficiency of the cycle, if you look at it. Then you have another case where you have 10 megawatts of heat, the 10 megawatts of heat that is available, but you produce 3 megawatts of work, but you reject 6 megawatts of heat. In the first case, you have rejected only 3 megawatts of heat. So if you look at it, the thermodynamic efficiency of the cycle is 33%, which now if you ask somebody and see that which one is efficient, then probably they'll say, okay, the case 1 sounds better because it has a higher thermodynamic efficiency. But when you're looking at a waste heat recovery cycle, your heat is waste. You're not paying for it. So really what you need to look at is thermodynamic efficiency is the wrong metric. The recovery factor, how much of it is you're converting into useful work, is the most significant most significant parameter. Unfortunately, that seems to be missed out by many of us who do these analysis. So for a waste heat recovery cycle, cycle 2 certainly makes more sense than cycle 1, although it has a lower thermodynamic efficiency. Okay. So why is it so important, and this background is important for supercritical CO2 is because, I'll quickly go through these slides. So supercritical CO2 cycles, you can actually tailor the number of heat exchangers such that you can now have pinch which are identical on the hot side and the cold side. So some of you who are into heat transfer research will realize that it is nearly impossible to have the same delta T throughout, in heat transfer between the hot and cold fluids. Then you get very high efficiencies. So in an SCO2 cycle, you can really ensure that you can extract the maximum amount of heat from the working fluid. So in that sense, SCO2 cycle certainly makes sense to, and that is why a lot of research is going on to see how to engineer an SCO2 cycle that you can extract the most amount of heat in the most efficient manner. Okay, so this is some of the work I'm going to skip through in the interest of time, but so this is one of the work that we have actually proposed, and we have filed an IP for it. So if you look at a waste heat recovery cycle, now we can actually push the recovery limit to about 30.4, 22.8%, which is the highest compared to any other any other cycle that is commercially available for SCO2. Okay. So now let's look at the biggest concerns or the impediments to realizing the SCO2 cycle is the design of the heat transfer equipment. So this tells you that if your compressor efficiency from isentropic efficiency of the compressor drops from, say, 1, that is 100% isentropically efficient compressor, to about 0.8, then you realize that, I don't know whether it's visible, but you can see that the amount of heat that is rejected in the gas cooler and recuperator significantly increase. Okay, so that means that the efficiency of your compressor also governs how much amount of, what is the size and capacity of your heat exchangers, and these heat exchangers are prohibitively expensive. Okay. Similarly, if you now look at the gas cooler exit temperature, that means that you have under-designed the gas cooler and the temperature goes up. That in the sense it means that you have a higher pinch temperature differential at the exit of the gas cooler, and this also significantly affects the cycle performance and you get a drop in efficiency. And also, not only the temperature difference, but the pinch temperature difference, also the pressure drop, because you're now operating at a very high pressure. So any amount of pressure drop that you have forgotten to arrest at the heat exchanger can significantly result in a penalty in the efficiency. So you see what people have promised about 50 to 60% efficiency, in realistically, it will actually drop down and bring it lower than steam. Okay, so how are we doing time? 20 minutes. So if you look at the biggest problems in SCO2 and what has been reported in the literature and where people have worked is closer to the critical point, your CP becomes very high. So people talk about how to design recuperators and heat exchangers or the turbo machinery, the compressor particularly closer to the critical point. But I think as an engineer, and that's something that a message that I would like to drive down to every engineer who feels that they're first engineers and not researchers, then something that is not well understood, stay away from it. Okay, so the properties near the critical point are thermodynamic properties. They're not measured because there is no means for us to measure. We don't even know whether the critical point exists. It's an artifact of the saturated vapor curve and the saturated liquid curve that actually merge. So when you don't understand, stay away from the regions where the data itself is uncertain. So what we did was, we decided that we will actually design our equipment where we are very clear about the thermodynamic properties. So we moved away from the critical point and said 90 bar is the minimum pressure that in the cycle that we would operate, not 73 bar. And this is actually, the whole world is moving towards this proposition now that they're operating closer to 90 bar and 95 bar because the properties are well known compared to close in the vicinity of the critical point. So this again just tells you that how the thermodynamic properties, the humps or the pseudocritical points keep on changing and reasons why you should not be operating closer to the critical point. So I'm keeping this part of research on what happens closer to the critical point for my rainy days when I don't have any funding, then we'll start looking at what happens to heat transfer equipment in the critical point region. Okay. Now another reason is how heat transfer is such a critical aspect in SCO to Brighton cycle heat exchanger designers. So you would always want the pinch to be located at one point, the cold inlet of the heat exchanger. Very likely, if you have the wrong selection of the pressure and temperature, then you might actually end up with an internal pinch. An internal pinch means that the large part of your heat exchanger is actually rendered useless. If there is a crossover, then there is no heat transfer that takes place. So you end up losing a large surface area of the heat exchanger, which is just redundant but adds to your pressure drop. So you have to very carefully design and not over-design. This is some place where heat exchanger over-design can be significantly major drawback in your equipment design part of it. You should never design a heat exchanger. You can have a margin in terms of pinch, but it should never be over-designed. So this plays a critical role in the SCO2 technology realization. So we have got now a full-fledged microchannel heat exchanger design code where we can get the full stack size. So let me just quickly go through it, quickly just skip through it. So we can tell you holistically that if you have a given power level, then what should be the stack size and what should be the channel dimension that will give you the minimum footprint and the cost of manufacturing. So it includes a lot of CFD analysis as a backbone that supports this analysis, where the heat transfer coefficients are generated from a high fidelity CFD model on a unit cell, and then it scales up to a thermal resistance network model for whole stack. So what we did was, we thought that, okay, why not, since we have the design code for making the heat exchanger, let's actually build and manufacture this heat exchangers. So we started manufacturing this diffusion bonded heat exchangers, and we have failed in 3 heat exchangers till date. So every heat exchanger burns a hole in the pockets. 15 lakhs is just gone. The moment the pressure drop fails, that means that one of the internal plates has actually opened up. The bonding between 2 layers of the plate has opened up, and that heat exchanger is virtually useless. It just cannot be repaired. And we are building the smallest heat exchangers, which are about 1 cubic feet is the dimension. And that's the smallest scalable size of a heat exchanger that you can build. So you see here, it's virtually impossible in this matrix of very fine channels to find out where there's a compromise in the bonding strength. So it has been prohibitively expensive. So we have not had too much of success till date, but we are still hoping that we'll continue to work and someday we will succeed. So on the turbomachinery design, the turbomachinery issues, we realized that most of the loss models that stem from are either validated with air or steam. But when we realize the kinematic viscosity of carbon dioxide is 1 order lower than that of water or steam, or steam or air, then what happens is the loss models in the conventional turbomachinery that have been derived and validated with air or steam actually do not work with SCO2. So we had to start looking at developing our own loss models and generating the very famous Balje chart or the NSCS diagrams, which tells us at which point in the non-dimensional NSCS diagram that we are operating. Okay. So I will go quickly. We also are now looking at work on all sorts of turbomachinery. Okay. So this tells you some design philosophy on how to design a radial turbine. So we also look at this probably. I'll take care. Okay. So we are now developing our own blade profiling tool. So this is based on an in-house MATLAB-based algorithm that is coupled to a ref prop, and then we use a B-spline curve to generate the generate the curvature for the blade. So this just tells you the profile generation. So this is generated using our own in-house mainline code, whereas the one that is on the right side is actually generated using a standard state-of-the-art industry standard tool called Axstream. Okay. So I have a student from NAL who is also looking at axial turbines. So on axial turbines, we are also looking at extending the through-flow solver for axial turbines, which is similar to the gas turbine. And you won't believe that the entire stack size for a 10 megawatt SCO2 turbine is about this size. What you see here, it's only about end-to-end, bearing end-to-end is about 300 millimeters. And the blade height is about the size of this mic, the tip of the mic. So the major problems is flow separation at the leading and trailing edges. So we're looking at arresting the flow separation at the leading and trailing edge. And frankly speaking, in supercritical state, I don't even know whether the separation would really occur or not. So this is another area of research that has really baffled us. So we rely on CFD tools, heavily on CFD tools, but on CFD tools it's just blind faith and belief that what the tools are giving you, the colored plots, is actually the physics that it is representing. But I think experimental testing of the plate profiles is something that one needs to look into. Okay, so I'm going to go quickly over this part. So, we had issues on materials. What would work with supercritical CO2? Ultimately, at the end of it, you have a machine and you have to build the turbomachinery, so we should know which materials are suitable, which will work. So there have been reports in the literature, and mind you that these reports suggest that there is erosion and corrosion of certain blade materials. But then one of our mandate that we wanted to make in India was that we didn't want to rely on nickel steels or internal steels which are imported. We wanted to make everything in carbon and stainless steel steels. So we actually developed an entire facility for doing corrosion studies on steel. And then we were able to monitor the corrosion rates for different, at different time scales. And this is what we did. I'll just go quickly. So there is one, okay, maybe that part I'll put in that. Okay, now I think I want to spend a little bit of time on this part of it, that what was our journey in terms of the turbomachinery realization. So maybe for 5 minutes I can take on this. So in the last 3 years, we have actually had about 20 design iterations. We built a few, didn't work, so we went back to the drawing board to see and figure out what really is happening. Okay. So first thing is, we realized that what we need is the selection of the power rating. Our test loop, what we have at IISc, can support about 20 kilowatts, but we realized that we don't get a feasible design at 20 kilowatts, so we bumped up the power to about 40 kilowatts to keep our speeds, shaft speeds, reasonable shaft speeds of about 40,000 RPM. Otherwise, we have to go over 100,000 RPM. So this is the first turbo machine that we looked at and we designed, and then we have this dry gas seal that actually prevents the high pressure carbon dioxide from entering into the compressor, the division that near the motor. So this was all an integrally single system, so that in case there is a leakage, nothing bursts off. Okay, intrinsically safe design. Then we realized that a lot of heat from the turbo machinery was actually, coming to the dry gas seal area, and the manufacturer was complaining, saying that, look, you have to keep the seal temperature lower to 130 degrees Celsius. So we ended up actually incorporating a radiation shield, and with every addition of components along the shaft, axial direction of the shaft, it actually started increasing the complexity of the entire design. So you see from design 1 to design 2, the length has actually increased because we started adding components to it. Okay. Then we also realized that our generator, we had significantly high viscous losses. So we had significant drag losses because we are now spinning at close to about a surface speed, so close to about 200 meters per second on the rotor surface, which was causing very high shear of the air that was entrapped within that 1 mm region. So now we had to reduce and we had to cool that. So we ended up actually having a large water jacket around it, and modeling this heat transfer coefficient was a very difficult task in this part as well. Then eventually we realized that there's a lot of conduction through the shaft itself. So then we ended up drilling a hole in a 500 millimeter, half a meter shaft, and then trying to incorporate a cooling jacket right up to the impeller end on the shaft. So this was another design iteration that we ended up doing. And then again having elaborate cooling arrangements to see that you can actually push the fluid inside. So this is some parts of it. So this works as a thermosiphon. So because rotation itself, the fluid is actually entrained inside. Then finally, we had issues with rotor dynamics. We realized, in hindsight, we realized that the shaft length kept on growing. Now we started having this rotor dynamic issues. So now we no longer could go with the bearing configurations that we had originally planned. So we ended up with a tandem bearing configuration, and the power levels also went up just to ensure that we are now able to get some respectable shaft power at the end. So this is another part where we had very high axial thrust loads and the bearings were not available for it any longer. So we ended up actually bringing a labyrinth seal to ensure that we can now reduce the thrust load at the back of the impeller. Okay, so this is the final configuration that we are now looking at, whether we can ensure that this can be realized. Okay, so this is some things, in the interest of time I'll just skip. So we have a student who's working on the labyrinth seal design to ensure that thrust loads are kept in control. Okay, this is some things on rotor dynamics. So these are the mode shapes. Somebody who understands rotor dynamics will actually appreciate. Then we had to do a lot of rotor dynamic studies, and the fact is that everything had to be done in-house. We now ended up actually doing most of the work ourselves. Okay. So this is finally the turbo machinery that is currently under manufacture. Okay, we are hoping that in the next 3 months or so we'll start assembling this turbo machinery, then we'll do the spin test. So this works at 60,000 RPM, develops 60 kilowatts, and everything that you touch is super expensive, but I hope that once it is productionized, price will come down. But just to give you a flavor of how expensive the system is, 5 bearings, each bearing is about 40,000 rupees. So if it fails a spin test, you have to replace all the 5 bearings. Okay, and the way that the spin test fails is that you'll get a small noise where your blade or impeller can rub against the housing, and then that's it. Then all 5 bearings have to be replaced. Okay, this is one prototype which we built. It didn't really work. 5 minutes? Okay, all right. So let me now, so this is the test loop that we have at IISc. Okay, I have a 2-minute video. Is that okay? Can you play the video, please? Along with the sound. Okay. So this gives you a summary of the entire. No, you should play sound from the computer. No, no. No, it should have played. You have to use source audio. You have to use. You have to give source audio. I mean, source audio is a thing there. Or they can play it there. And no. Or you play the video. Video see my hand. Maybe source audio. I don't have it separately. You can play source audio. Use computer source as well. Audio source. So this gives you the exact SCO2 test loop. So I have a video of it.
Density and favorable transport properties of supercritical CO2 makes the power block extremely compact and efficient compared to a conventional steam system. The cycle begins by compressing the CO2 from 75 bars to 120 bars. The high-pressure CO2 is passed through a microchannel heat exchanger-based recuperator to recover heat from the high-temperature CO2 from turbine exhaust and heat the low-temperature CO2 from compressor discharge. The test loop employs a two-stage heating system to heat CO2 leaving the recuperator to 535 degrees Celsius. The first stage heater serves as a replacement for recuperator during startup when recuperation is absent. In an actual installation, the second stage heater is replaced by a suitable heat source such as concentrated solar power or a waste heat source such as gas turbine exhaust heat. During the process of heat addition, high-pressure CO2 undergoes significant density change, thus significantly reduces the volumetric flow rates across the turbine and shrinking the size of turbomachinery. CO2 at 120 bars and 535 degrees Celsius enters the turbo generator to generate power. The low-pressure, high-temperature CO2 passes through the recuperator before passing through a micro-channel-based gas cooler. Water is used as a cooling media in the gas cooler. The cold CO2 is routed back the compressor suction, thus completing the cycle. The realization of SCO2 technology comes with a lot of hurdles. Small blade heights in turbo machinery poses key challenges in sealing and manufacturing. In very high operating speeds ranging from 40,000 to 150,000 RPM, makes it an engineering nightmare to realize the technology at small scales. The group at Indian Institute of Science is addressing these issues by designing novel labyrinth seal arrangements to reduce the pressure and leakage to minimize the impeller thrust load and increase bearing life. The CO2 turbine employs a dry gas seal to seal the processed CO2 from leaking out. Numerous cooling arrangements have been analyzed to maintain the DGS temperature within specified operating limits. Rotor dynamics and structural integrity of the shaft are critical aspects of high-speed machines. Number of rotor configurations have been simulated to optimize the shaft dimensions to mitigate operation near the critical speeds to ensure safety. The work is financially supported by Department of Science and Technology, Government of India. The extensive technical interactions with Triveni Turbines Bangalore has significantly contributed to the development of the technology.
Thank you.
Thank you, sir, for your invaluable insights and overall informative talk. I now request the Senior Chair, Dr. Sachin Singh Gautam, to felicitate Dr. Pramod Kumar with a token of gratitude and a memento. I also request Dr. Sikrawar and Dr. Pallav Gupta, sir, to accompany our guests. I also request Dr. R. Gityagi, sir, to accompany our guests for the felicitation. Please put your hands together and give a huge round of applause as we felicitate our esteemed guests. Thank you so much, sir. Thank you, sir. Thank you so much for your presence and a very valuable talk. We are now beginning with the technical sessions. I request all the presenters to provide their presentations to us at the backstage. I request the session chair, Professor Dr. Sachin Singh Gautam, sir, to kindly take their place on the dais. I also request Professor Dr. Pallav Gupta, sir, to take his place on the dais. I welcome our esteemed guest and the session chair for this technical session, Professor Dr. Sachin Singh Gautam, sir, Associate Professor, Department of Mechanical Engineering at IIT Mandi. Dr. Sachin Singh Gautam, sir, is currently working as an Associate Professor, as I mentioned, at the Department of Mechanical Engineering at IIT Guwahati. He primarily worked in the area of dynamic adhesive contact problems, developing novel time integration schemes. Before that, he finished his PhD in mechanical engineering from IIT Kanpur, working with Professor P.M. Dixit in the area of simulation of high-impact fracture using continuum damage mechanical model. He has published 3 book chapters, 10 journal papers, 35 conference papers, and 2 referred conference proceedings, and 5 journal papers are currently under review. His current area of research is in nonlinear finite element analysis, computational contact mechanics, isogeometric analysis, adhesion, and GPU computing. He is also working with the VSSC ISRO Trivandrum from developing a contact model from their FE software feast. We welcome you, sir, to our technical session. As we proceed with the technical session, I also request Dr. Sachin Singh Gautam, sir, to kindly come to the dais and bless us with some of your insights.
Yeah, so good afternoon everyone. We are running short, so welcome to this technical session number 1. In this auditorium we have around 17 some papers, and I guess the speakers have given their presentations to the desk here. And with not much further ado, I'd like to start. Mine? Yeah. Okay. So as was already told, I'm Associate Professor of Mechanical Engineering at IIT Guwahati, and I primarily work in the area of computational development of computational algorithm development. Primarily, I'm doing work for VSSC ISRO for their Make in India software fees, and we have developed isogeometric contact analysis module for them. And there are 3 more modules that we are developing for them: a caustics module, hyperelasticity module, and our aim as such is to have a Make in India software. It's already there to enhance its functionality. So in case we are under some embargo in future, we should not be lacking any finite element software of our own. So that's our objective that we are currently working on. Of late, started working on machine learning. That's a bread and butter now. So with this information in hand, I guess we can start. Okay, thank you. So I'll take
Thank you, everyone. Thank you, sir. Now let us move to the next phase of this session, and let us call all the IDs which are present here to present their papers. First, let me call the paper ID 15 on the podium and give his thoughts about his paper. Thank you.
Hello, ladies and gentlemen. This is Sopon Purwa from NIT Durgapur. Okay, but all right. But you have not mentioned the time for that kind of things. You have not mentioned the present how much mention you have not given. All right. So what I'm trying to present here, right from the inauguration up to the last keynote session, I'm able to learn something that machine learning, then it is bubble dynamics, CFD, then it is supercritical carbon dioxide. And one thing here at this conference, this learning in aspect of mechanical engineering, whether it should be driven by theory or it should be driven by the learning from example, that is called the machine learning. That is one resolution we have to take up. As I am simple that I believe I should start from the theory. I will prove that how it is important compared to that machine learning. Because you see that is one continuum approach, one quote. A continuum approach is of more immediate interest to the engineering students. I mean, if you are trying to formulate one problem, unknown problem, and if you are trying to solve with using exact solution method, you can find out what you are trying to do. That is what we need for the strong theory backup. And that will help you to understand all this machine learning or CFD, whatever you are trying to do. That's why I'm saying the theory is the backbone of all kind of CFD and machine learning. That's what I'm trying to say. So my present topics is that analytical solution of heat transfer in laminar flow of a single phase liquid through a microchannel. I have solved many problems in the normal conventional channel, but at the same time I have seen that I have not handled that diameter, flow channel diameter is of micron range or millimeter range. Maybe the point less than 10 millimeter, 1 millimeter or maybe the 1 micron. That I have not handled. People are using that. I have been. Can you see this presentation? I have been, slightly motivated by these two applications. One is that miniature application or miniature or nuclear reactor that is going to be attractive in the commercial use. up to 75 megawatt or 25 megawatt. I will see that in US National Regulatory Council and European Atomic Energy Commission and your Canadian National Security Commission and Chinese National Nuclear Commission, all these are trying to have very small reactor, or miniature reactor, or mini reactor, nuclear reactor, that will for the commercial use. That is one application that has attracted me. At the same time, there is huge application in the electronic device, the microchannel heat transfer cooling device. All these are application for the cooling of a particular hot bodies. So anyway, main advantage of this application is that you can have more heat transfer area per unit volume of the kind of this mini channel. That is one advantage we can exploit from the mini channel, and we have very high heat transfer efficiency. Now you have seen that there is, yeah. We have seen that this is the objective that I am trying to, one problem that I am trying to face, that when you are formulating this problem, that gives you the Sturm-Liouville problem. That Sturm-Liouville problem, if the eigenfunction is orthogonal, then you can solve directly, because you can have by the Bessel function. But at the same time, if this Sturm-Liouville problem does not apply, if it is a laminar flow heat transfer, I mean, if it is fully developed flow heat transfer, then it cannot be applied. You will not find that Sturm-Liouville problem, and that eigenfunction will not be orthogonal, and you will not find that eigenvalues very easily, exactly, by using the analytical method. You have to use the semi-analytical method or numerical method. Here I am trying to find out this solution. I am trying to reduce the complexity of the eigenvalues calculation by reducing the problem to the zero order Bessel equations. That is one of the motivation whether I can do it by using the analytical solution. And that is the then we have seen that there is some uncertainties with this when you are reducing to that zero order Bessel function. Then I had to switch to that solve this eigenvalues numerically at that time. Anyway, if you look at this channel, this thermal layer and this is the hydrodynamic layer, in the micro channel, there is one difficulty there also. You can find out that both the thermal layer and the hydrodynamic layer, they are superimposing in each other. It is very difficult to identify which effect is there, whether it is hydrodynamic layer effect or it is a kind of this thermal layer effect. Because that miniature configuration of that flow channel, it will be superimposing, and it will be confusing for the engineer to identify which effect is in the driving seat. So this is we are trying to identify. Here is the typical solution. I have just find out. First, I have simplified the problem by assuming that potential flow. Obviously, potential flow is a gross approximation that will prove, but it will solve some beautiful problem that I will show also. And this problem has been simplified from the complete equation from the Bar that transport phenomenon book, Bar. And with a couple of assumptions, I can see that this is the steady state, and it can be incompressible and fully developed, fully developed flow. So if you look at that, this equation, it has been reduced to the scaled form, that means non-dimensional form, and that will give you the series solution, and that series solution is containing that lambda that is called the eigenvalues. You cannot solve it very directly. Yeah. What is this? वो तो ठीक है, but आपको complete करना है ना, तो ठीक है. So what I can do here, so I have to reduce this problem to the Bessel function by using the potential flow that you can find the eigenvalues in terms of the zeros of the Bessel function. And these zeros of the Bessel function is available from the literature mathematical table. And you can solve this problem nicely, and you can define the Nusselt number like we have here. And then what we can do, then we have introduced the complication of laminar flow and at the same time we have taken the axial conduction. Microchannel, another important part is the axial conduction is very dominating. That means axial conduction is very dominating. When it is axial conduction is very dominating, then what will happen, that axial convection term will be very less. That means Peclet number will be very less for the axial conduction. And in microchannel, this Peclet number is very less. That's why I have to introduce this term, that axial conduction. You see that, and these two complications, one is the fully developed flow, another is the axial conduction, to find out that solution is, it is not the real Sturm-Liouville problem. You cannot solve it analytically, you can solve it numerically to find out the eigenvalues, and that we have done by using the shooting method, multiple shooting method, and obviously some numerical integration that you have been used. And this is the numerical result that we have, and you see that Nusselt number is decreasing with time, decreasing with the axial distance, and it goes to the asymptotic value for that. And now you can see that these are for the potential flow. These are for the potential flow, okay? And you see that these are for the potential flow. And next, what we have seen that this is the microchannel that we have taken from this literature, and we have seen that for the potential flow, if we see literature, that experimental data, I have compared with that potential flow and laminar flow, and this data, experimental data, is in between. That means laminar flow heat transfer is giving the minimum heat transfer rate, and the potential flow is the highest heat transfer rate, and the experimental data is in between. And it shows that the potential flow is not so bad that I can see here. But at the same time, this is a Gauss approximation. People will raise the questions. At the same time, I have done also for that laminar flow with that, where the viscous effect is very more. And you see that experimental data is matching on the analytical solution, where the CFD result is slightly debating. Where this is the standard, that you better rely on that theory, better put before starting up that CFD, all this machine learning, because it is the founding stone. It will make your backbone strong based on the theory. All right, this is the eigenvalues that I have computed, and this is the I have compared with the literature. They are very close, and for the fully developed and the axial conduction problem, eigenvalues has been solved by this shooting method, and by taking the initial guess of eigenvalues, I can match the boundary condition. It takes the couple of iteration. All right. And this is the conclusion, and you can see with the potential flow and the axial conduction, that is very close to the experiment, but at the same time, potential flow, previous one, the axial conduction and laminar flow is matching well with the experiment, but at the same time, the last conclusion is that potential flow is not so bad. It can be used for the liquid metal. That means liquid solvent coolant in the first breeder reactor. You can see that. What is that? For liquid metal, that thermal layer travels very fast to the this hydrodynamic layer, and it will give you that approximation can be useful here. Okay, thank you, and this is my contact number. All right.
Thank you, sir, for this amazing lecture. If anyone here in the crowd to ask some questions.
You have questions? Yeah. Anybody has questions?
Yeah.
Sir, I have just one query.
Yeah.
Am Am I audible?
प्लीज प्लीज बैठिए, आप बैठ सकते हैं. अरे गए, हाँ बोलिए. Yeah.
Sir, I have one query that how much is the Knudsen number of your flow?
Nusselt number at steady state, it is going to be depending on that whether it is viscous effect there, laminar flow is there or potential. Potential flow थोड़ा ज़्यादा होते हैं 5.18, and if it is laminar flow, that I'm talking about the asymptotic value, that will be 3.56.
अगर मैं मतलब इस माइक्रो चैनल में फ्लो की वेलोसिटी हम इतना बढ़ा दें, मान लीजिए हमारा माइक्रो चैनल का डायमीटर है 0.1 मिलीमीटर.
Yes.
अब उस 0.1 मिलीमीटर में अगर मैं
बहुत ज़्यादा वेलोसिटी कर सकते हैं.
रेनॉल्ड्स नंबर अगर मैं 10,000 कर दूं, 10,000 के इक्विवेलेंट में वेलोसिटी ले लूं,
that axial conduction term will be neglected because Peclet number will be very high. At the same time, axial conduction will not be very high. Axial conduction will be neglected, and that will perhaps it will affect this performance because that thermal entry length जो है ना, that will be reduced because in the micro channel, in the thermal entry length में बहुत ज़्यादा heat transfer होते हैं. That's the problem with the very high Reynolds number.
अगर मैं रेनॉल्ड्स नंबर बहुत ज़्यादा बढ़ा दें,
हाँ, it is going to be turbulent zone.
फ्लो रिजाइम में जाए तो टर्बुलेंट फ्लो रिजाइम में,
हाँ, वो तो नस्ल नंबर कम हो जाएगा.
How we will obtain the analytical solution for that?
कौन सा?
Turbulent flow अगर
No. Micro channel is normally operated to get the viscous effect, not the high turbulence.
नहीं, मान लीजिए हमने उतनी वेलोसिटी उसमें इंट्रोड्यूस कर दिया तो okay.
So we can enter because I got your question. Okay, thanks to.
Hello.
Yep. So the next presenter, paper ID 60, is he or she here? Okay.
What an amazing lecture it was. So I may now call the paper ID 94, Mr. Nandan Shukla. Please come on the stage.
Good evening, everyone. My name is Nandan Shukla, and he's my co-author Aryan Sheth, and we are going to present on the topic of waste heat utilization from data centers. So this is the flow of how we are going to look at the problem and its solution. So first of all, I would like to help you go through what we are going through in our mind. So we came across a problem that slowly and gradually in the last 2 decades, a lot of data is starting to be getting consumed, and we believe that as more and more data is being consumed and more data centers are coming up, lot of energy is going to be required to cope up with that. So in order to minimize that energy, we can use the heat from the semiconductors that are being used in the data centers, and we can at least minimize or we can regenerate electricity from the heat. So here you can see some statistics that we have found out, and you can see the amount of difference that is there between 2017 and 2020. So first we went on to do some research on how we can extract heat from the semiconductors. My co-author will continue.
So
basically, I would be first discussing what are the cooling techniques that have been used till now and are in the prevalent stages in near future. So there are basically four methods, and the first and the very primary cooling technique used is the air-cooled system. So as the name suggests, air is used to cool in these kinds of data centers. So as you can see in the diagram, the the cold aisles and hot aisles are formed due to the placement of the servers, and because of which from the CRAC, that is the computer room air conditioning unit, the cold air is passed on to the cold aisle, and the uh, cold air then passes through the machinery and forms the hot aisles hot air that is collected back by the CRAC unit, and that CRAC unit throws it outside to the chiller, which throws that heat collected to the ambient environment. So this is basically how an air-cooled system works. So the second of them all is the liquid cooling system. So as the name suggests, in liquid cooling system we use liquid, and it can be water as well, a mixture of water and glycol as well, or it can be any different kind of coolant as well. So in this, it is very similar to air cooling systems, but the only difference is that what a substance we use for cooling is a kind of liquid. So the basic structure of the server would be the same. From the CDU, that is the coolant dispersing unit, the cool liquid would be transferred to the servers, which will absorb the heat generated by the machineries, and that will form the red lines, that is the hot air. So that hot liquid would then pass on back to the CDU, and that will pass it on to the chiller, similar to the air-cooled systems. And this way, the chiller will exert the heat it has collected, and so the ambient gets hotter. So basically, these are the major two limitations of the prior two methods, because it exerts the heat collected to the ambient environment, which can cause global warming as well as carbon emission. So these are the major limitations of the first two methods. Now the third method, and the best of them all, is the two-phased cooling system. So in two-phased cooling system, the cold coolant is passed on to the machine and the tank, which is shown in the image. So there it is heated, and because of the heat, it gets converted into the vapor form, and that vapor form passes on through the diagonal lines that are shown in the image, and they get condensed in those lines. And because of that condensation, the vapor is condensed and formed back to the liquid state, and that liquid is again passed on to the dispersing unit, and this way the process keeps on cooling for the two stages, and that is why the name is two-phase system. And this is the best of them all. And the fourth method that can be used is a hybrid cooling system. So hybrid cooling system is a combination of compressed vapor method and also the water or say liquid method. So as you can see in the image, the right side is the basic air cooling system, which we saw in the first section, and the left-hand side is the two-phase method. So both are combinedly created in the data center, and as and when required, according to the season and the requirements of the data center, we switch between the air-cooled and the water-cooled systems. So that is known as the hybrid cooling system. And the problem now that we have discussed that how the cooling systems and cooling techniques work in the data center, so what is the major problem that we would be justifying in this research paper? So basically, as you know that the fuels that we are using are some way or the another way in near future gonna degrade, and also it is declining in a steep rate. So because of that reason, we need to utilize the fuels that we are using, and also the heat that is generated by these cooling systems is dispersed to the environment, which causes harm to the environment as well. So if we can utilize somehow this heat generated and exerted to the environment to generate electricity or to cut costs, then this could be beneficial for the data centers and save around millions of dollars. And because 50%, more than 50% of the power used by a data center is for the cooling, so if we can use that heat that is exerted to the environment, that is completely wasted. So rather than wasting, we could utilize it to generate electricity or to cut costs. So this is the main problem formulation, and the methods that would that we have found that can be implemented in this method so as to utilize this waste heat and to utilize it to our benefit is presented in the later subsection, and I would like to call Nandan for presenting it.
Yeah. So there are several methods. Due to shortage of time, I'll go through them quickly. So first is district heating. So the low quality heat is it cannot be used directly anywhere. So the low quality heat is pumped into the district heating water heating system, and the Nordic countries require a lot of water heating system, and they spend a lot of money on that. The water from data centers can be directly used there. Next method is water heating for the power plants. So electric, like the power plants require a lot, thermal power plants require a lot of preheating to increase the efficiency. So we can use this low quality heat to heat up the air in the thermoelectric power plant. So the next is absorption cooling. So it basically does not utilize the heat, but it reduces the amount of heat that is being generated. It basically uses the same heat and uses the phenomena of absorption of heat, and it reduces the amount of heat that is released into the environment. Next one is piezoelectrics. So piezoelectrics is basically applying mechanical stress to any to a device and generating electricity out of it. So we can use the thermal, heat that is generated out of data centers and can use it in for like generating physical stress into piezoelectric devices. We can use Seebeck effects as well. So Seebeck effect is one side heating and one side cooling of a material, and it can generate electricity out of it. Another method is utilizing it in desalination plants, that is using like taking in seawater and separating out fresh water from it. We can co-locate biomass plants and use the same heat in the biomass gas production. We can also use organic Rankine cycle to use the low quality heat on organic fluids to generate electricity. And based on these findings, based on this research, we come to a conclusion that the different methods can be used at different places, and it does not necessarily there is no necessarily the best method for utilizing heat at a particular location. Thanks a lot. I'm open for questions and answers.
Any questions from the audience? Okay, thank you. Thank you so much. What wonderful thoughts of saving heat from wastage. Now, I may request, there is a request from to all the participants, please keep your presentation from 10 to 11 minutes because there is a shortage of time. So now I may call ID number 551. Please come on the stage.
My name is Maxino Kamcha, and today I'm going to talk about the topic ultra broadband with high absorption rate. metamaterial absorber on thin substrate for airborne radar applications, and this work is done under the guidance of Professor Malayaranjan Tripathi. And this is the overview of my slides. I have included the introduction and then the designing of the metamaterial absorber, and then simulation results and discussion. After that, it is followed by the conclusion and references. So absorbers are special materials like a rubber base, which are designed to offer a user-friendly approach to the reduction of the unwanted EM radiations from any electronic equipments. And metamaterials is any specially engineered materials that has a property that is not found in the naturally occurring materials that are made by assembling these multiple elements arranged in repeated patterns. And metamaterials, due to their precise shape, geometry, size, orientation, and arrangement, they give them their properties that is capable of manipulating EM waves by blocking, absorbing, enhancing, or by bending the waves. And here comes the designing of the metamaterial absorber. This structure has a 9 cross 9 millimeter square dimension, having a thickness of 2.7 millimeter of FR4 substrate, and it is composed of 3 layers. The top structure that we see here, the L shape, this is a top structure, and the middle one is the FR4 structure, and the base is the ground. And for the simulation results, figure 2 is the absorption and reflection for the suggested MMA. Here we see the red dotted lines here. This is the reflection coefficient, and the green one is the absorption rate. The red one here has the S11 of less than minus 10 dB from 7.9 gigahertz up to 17 gigahertz, with the absorption rate above 90% over all these bands. And this figure 3 is the effect of different polarization angles on the absorption rate. Here in this figure number 3, we have seen that while changing the angle of incidence on this structure, we have seen there is changes in the absorption rate. Here the solid color on top above the 0.9 is the absorption rate. While we change the incidence angle from the 0 to 15 degree, we don't see much changes in the absorption rate. But when we increase this absorption, when we increase this angle, we see that there is reduce in the absorption rate, and this reduction is due to the lack of fourfold symmetry in this structure. And this is the comparison table of the metamaterial absorber. The first one is taken out from the reference number 6, and it has a dimension of 11 cross 11, having absorption rate of only 90%. Like this, in this work, we have a dimension of 9 cross 9 millimeter square, having the frequency range from 7.9 gigahertz up to this 17.6 gigahertz, having the absorption rate above 90%. And in this figure number 4 and figure number 5 shows the electric field distribution and the magnetic field distribution at different frequencies at 8.392 gigahertz. We see that this at this frequency, electric field is mostly distributed at the edges of this resonating structure, and in the magnetic field distribution, we see that this at 8.392 gigahertz, we see most of the field is in the corner of this L-shaped resonators. Just like this, we have done for 11.332 gigahertz and 15.844 gigahertz also, and we can see how at this gigahertz we have seen how they have interacted with this electric field and the magnetic field. And this figure number 6 is the surface current distribution, and here also we have checked which of the parameters is responsible at this specific frequencies. And then we have checked the parametric structure, and then we have changed the parameter of these L-shaped structures, and then we have seen the absorption rate, changes in the absorption rate. Here at A, we have changed the vertical dimension of L-shaped, and in this B, we have changed the base dimension of the L-shape, and we have seen that there is fluctuation in the absorption rate. Likewise, we have why is this changing so fast? Likewise, in this figure number 8 also, we have changed the base width L1 and the base length W1, and we have studied the changes in the absorption rate. And in this figure number 9 also, we have changes this L2 and W2 and studied the absorption rate also. And in this figure number 10, we have changed the thickness, that is height of this suggested metamaterial absorber, and we have checked the resonance at height when height is equal to 2.3, 2.5, 2.7, 2.9, and 3.1. Here we have seen that at 2.7 it has given the best results here, so this has been optimized to height of 2.7. And in the conclusion, we have designed an ultra broadband with a very high absorption rate MMA with 9 cross 9 cross 2.7 millimeter cube. And in the simulation results, we have seen that the radiation is below this minus 10 dB from 7.9 to 17.06 gigahertz with the absorption rate over 90% in the entire frequency ranges. The substrate thickness is only 2.7 millimeter, adding a feature of this design, making it to a low profile and less bulky components that can be widely used for appropriate microwave applications. And these are my references.
Any questions from the crowd? Okay, thank you, Mr. Maxon. What beautiful thoughts on a new material. As we know, always, new material leads to growth of our nation. Now I call ID number 90, Miss Vartika.
Good evening, everyone. I am Vartika Gupta, PhD scholar at Panglatan University, standing before you to give my presentation on my review paper, which is the impact of heterogeneous catalyst on bad vessel production, a review. my content, which I'll be covering in the presentation. Introduction part. As we all know, fuel supply is the vital for human growth as well as well-being. The global energy consumption has increased to approximately 12 billion, and its demand is increasing day by day, which cannot be counted. The growing population demands for luxurious life and higher living standards, and for that they require fuel energy, which has increased the crude oil price and therefore has also affected the world economic activity. In today's world, fossil fuels are consumed 80% in primary energy consumption, of which 50% in transportation sector. This has led to various environmental issues causing global warming and several other environmental factors. The chart alongside shows that the global energy consumption has shown a quite increase year by year. Thus, it is an alarming time to look for an alternative source of energy to meet the increasing demand. Due to energy security awareness, biodiesel is popularized on the global fuel market. Now, biodiesel is a fatty acid alkyl ester which is derived from waste resources like animal or plant fats, vegetable oil, etc. There are various processes which are studied for its production, like microemulsification, blending, thermal cracking, and transesterification. But conventionally, we use transesterification method because it is easier method to use and give higher biodiesel yield. The term bio defines renewability, and diesel indicates its use as fuel. Biodiesel production. As we all know, biodiesel is a step-by-step production. The figure alongside shows the flow chart of biodiesel production. The catalyst and alcohol are mixed with oil or fat. If the FFA content of fat is less than 2.5%, we can directly use it. But if it is higher than 2.5%, we need a pre-treatment that gives a neutralized oil. Then a transesterification method is followed by phase separation. Then crude biodiesel is produced, and then after purification and quality control, we get a biodiesel which can be used for further purposes. And what is transesterification process? Transesterification process, also known as alcoholysis, and in organic chemistry, it is defined as the process of which organic group R of an ester is exchanged with organic group R of an alcohol, which can be shown in the equation of transesterification, which shows that the triglyceride with methanol gives methyl esters and glycerol. Now, catalyst. A catalyst, which we are all studying from class 6th or 7th, the day we have studied chemistry, is a substance which accelerates the rate of chemical reaction without affecting itself. Catalyst can change the speed of reaction that are carried out thermodynamically and provide directions on the progressive rate of experiments. The catalyst can be homogeneous or heterogeneous or biocatalyst. For homogeneous catalyst, there are acid catalyst and base catalyst. For heterogeneous catalyst, they are base heterogeneous, acid heterogeneous, and acid-base heterogeneous catalyst. Now, literature review. I have studied for the papers for writing this review paper, in which Evera et al. Studied about both edible and non-edible oils, and in that he concluded on base of cetane number and iodine value that methyl esters obtained from palm and coconut oils were not suitable to use as biodiesel in cold weather condition, but for hot climatic condition, biodiesel obtained from remaining oil sources is suitable. Kataria et al. Investigated the biodiesel production from waste cooking oil and studied its operational characteristics on variable compression ratio. The optimum conditions were 12:1 methanol to oil ratio, 5-8% of catalyst, of zinc dot calcium oxide catalyst, and they have produced a high biodiesel yield by this process. Rashid et al. Studied the production of biodiesel from waste cooking oil using heterogeneous catalyst derived from CEO eggshell. In this, he has used for the production of CEO the waste eggshells and has produced it as a heterogeneous catalyst. And the highest conversion of 96.11% was obtained at 30:1 methanol to oil ratio at 65-degree reaction temperature through 3-weight% catalyst loading for 3-hour reaction time. Objective of this research. In this review paper, authors have discussed about how several types of heterogeneous catalysts can be used for the production of biodiesel, and have also discussed about its effect on the biodiesel yield. The authors have also mentioned about the problems that arise while using homogeneous catalysts, as homogeneous catalysts cannot be reused and also have low yield. The aim of this research is to discuss both technical and economic aspects for the production of biodiesel using heterogeneous catalyst. Now, what are heterogeneous catalysts? Heterogeneous catalysts are catalysts whose the phase of reactant products are different from the products. Now, why should we use heterogeneous catalyst? Heterogeneous catalyst plays an important role in industrial chemical production due to their robustness and low operational cost. Moreover, in particular, through easier recovery or separation from the products, allowing chemical process to be streamlined. Now, there are various types of heterogeneous catalysts. First of all, we'll be going through heterogeneous alkaline catalysts. Metal oxides are usually heterogeneous alkaline catalysts in this study. Several metal oxides, namely calcium oxides, magnesium oxides, have been used in this research. CO was found as the most effective base catalyst due to its low FFA content and has given a higher biodiesel yield. Moreover, heterogeneous alkaline catalysts give better performance in transterification process. However, they have one disadvantage also, as it absorbs moisture during storage and have affinity to water. This table shows the various reactions which were carried out by various researchers and shows the effect on production of biodiesel and a different transterification process using heterogeneous alkaline catalyst. Now, heterogeneous acid catalysts are comprised of heteropoly acids, zeolites, and modified transition metals such as silica, alumina, zirconium, and molybdenum. The idealist characteristic of heterogeneous acid catalyst is it should have major active sites, porosity, and water repellent, with an aim to minimize diffusional issues. The table alongside shows the effect of various heterogeneous catalysts for the production of biodiesel, which is carried out by various researchers I have reviewed. Now, heterogeneous acid-base catalyst. It has been observed that heterogeneous catalysts which possess both acid and base characteristics could esterify FFA and transferify triglyceride to biodiesel simultaneously. It has been observed that among other side acid-base catalysts, CaO and La2O3 give highest yield and highest stability. The chart alongside shows the various research work for the heterogeneous acid-base catalyst. Now, heterogeneous biocatalyst is a new and applied method which has solved many problems related to environment, high yielding cost, and high energy requirement. Unlike heterogeneous alkaline catalyst, biodiesel catalyst does not result in foam formation, thereby can produce biodiesel with materials of low quality. The chart alongside shows the transterification reactions by using biocatalysts for the biodiesel yield. Future prospect. Recent studies are on the exploration of the eco-friendly approach due to several hazardous environmental factors, especially greenhouse effect, which is degrading the environment a higher rate than it can recover. This has led researchers to find different ways of generating energy without disturbing the environment, that is renewable environment. Biodiesel nowadays has grabbed everyone's attention as it is a green fuel. Unlike homogeneous catalysts, heterogeneous catalysts provide reusability, low production cost, and comparatively higher percentage of biodiesel yield even under normal transterification condition. Major findings for the production of biocatalysts: calcium oxide is found to be most extensively used metal catalyst, potassium and sodium hydroxide for the acid catalyst, sodium silicate for heterogeneous alkaline catalyst, and CaLO2 for heterogeneous acid-base catalyst. It has also found that the minimum yield of heterogeneous catalyst is 75%, which is difficult to use while using homogeneous catalyst. And in addition, it can be used for former, causing less wastage. Conclusion: biodiesel has turned out the best substitute over the non-renewable source of energy. The advancement in heterogeneous catalysts has sorted the problem with homogeneous catalysts and also enable economic development, thus decreasing the cost. The use of green source as its heterogeneous catalyst decrease the cost of production, thereby increasing the cost output. These catalysts lower the activation energy, reaction time, hence decrease the production cost. These are the references I have gone through, and that's all from my side. Any questions, please?
Any questions from the audience? No? Okay, thank you, Vartika. Many people don't want to give up on IC engines like petrol or diesel, and this idea of biodiesel is a great achievement. Thank you. Now I would like to call ID number 20. Please come on the stage.
So good afternoon, everyone. So my paper ID is 20, and the title of the paper is Estimation of Lacunocananular Permeability in Anatomical Region of Femoral Cortex, Endocortical versus Perosteal regions. So these are the outlines. So first of all, I'll talk about the motivation, then introduction, then the methodology, resultant discussion, then conclusion, and at last references. So as we know, bone is a biphasic material which adapts changes whenever mechanical loading is applied. So in 1960, Frost has given a theory of mechanostat. So according to this theory, whenever there is a disuse condition, the bone mass will get decreased. Whereas there is normal activity like walking, jogging, swimming, the bone mass is maintained. And whenever there is an external stimulus, means if you are applying more than the physiological limit load, then the bone formation will enhance. So as we know, osteocyte, osteoclast, and osteoblast regulates the osteogenic activity. So osteocytes is a mechanosensitive cell which is used for bone formation, and then osteoclast, which is responsible for bone resorption process, whereas osteoblast is responsible for new bone formation. So bone gain versus bone loss. So as you can see at the left hand side, the dominant arm of the tennis player is having higher cross-sectional area as compared to the non-dominant arm, whereas the bone loss can be observed in case of astronauts, physically challenged people, spinal cord injury, or bedridden patient. So the consequences of bone loss will be there will be increase in porosity and reduce in cortical thickness, which leads to bone fracture. So the solution, one of the solution is pharmaceutical drugs like bisphosphonate, calcium. But according to the literature, if you will absorb the bisphosphonate or calcium, it will adverse the remodeling process. So the alternative is natural therapy, that is nothing but physical exercise. So low amplitude cyclic mechanical loading may inhibit the bone loss. But how and where to stimulate to maximize the osteogenic response? So here the osteogenesis is nothing but the new bone formation. So how and where to stimulate means at which point we should apply the load, or which type of exercise we should design in order to enhance the bone formation in case of bone losses. So that is very much important. So the relationship between loading induced mechanical involvement and site specific new bone formation is less clear. So that means if let's say the bone loss occurs at this point, so maybe the orthopedic surgeon will tell you a standard protocol like you have to consume these medicine and you have to do these regular physical exercise. But when you're talking about the sports biomechanics, at that time we have to provide the site-specific new bone formation. That means we have to provide the accurate loading conditions in order to inhibit the bone loss or in order to increase the bone formation. So in literature, there are various in vivo loading configuration which have been used for bone adaptation, like axial loading, ulnar loading, 4-point bending, 3-point bending, cantilever bending, and knee loading. But the important question is about the computational model or numerical model, how much they are successful. So mainly the computational models fails to stimulate the new bone formation at different sites. So if you take a tibia, or you can take the tibia means the leg, and if you'll cut at the mid diaphyseal, you will get an annulus type of geometry. The inner geometry is known as the industrial, and the outer geometry is known as the perosteal formation. So the computational model mostly fails to simulate the new bone formation at industrial surface. So one of the possible reason could be the same microporous properties they are using for the computational modeling. So here what I have done, I have tried to find out the microporous properties or poroelastic properties in femur as well as tibia. So I have taken 30 Vista rats, and then at the mid-diapasal cross-section, I have taken out a slices of 3 or 4 and then with the help of epoxy resin, I have created, I have created the sample, and then I have done the indentation. So for indentation, I have marked the different surfaces like in anterior, posterior, medial, and lateral region, and then I have done the indentation from periosteal region to the endosteal region. So 4 indent I have done across all the regions. So these experiments is ethically approved by IIT Roper, and all the experiments have been carried out at IIT Roper. So then after obtaining the PhD data from the nano indentation, then I have used the ON and FAR method for nonlinear least square optimization. So as we know, for defining a poroelastic material, we need 5 properties. So if you're going to give the 2 properties, then the another 3 properties can be computed. So here the Skempton coefficient alpha and undrained Poisson's ratio I have assigned according to the literature, and then I have tried to find out the value of shear modulus, permeability, and Poisson's ratio. So first of all, I have imported the PhD indentation versus time data, and then I have given an initial guess, and then I have normalized the data. Then after that, again I have dimensionalized the data, and the difference between the normalized and dimensional differences I have computed in order to find out the remaining properties. So this is the, you can see the force versus deformation diagram at periosteal as well as endosteal surface, and we have computed for different anatomical for different regions like an anterior, posterior, medial, and lateral. So as you can see, for different regions within the same bone tissue at different regions, we are obtaining different indentation curve. This is the deformation versus time graph. So now the result and the results. So as you can see here, the shear modulus, you can see for femur as well as tibia, they both are having different shear modulus, and at different anatomical locations, means anterior, posterior, medial, and lateral also, it will have the different properties. Similarly, for the permeability, it can be observed that the endosteal surface is more permeable as compared to the periosteal region. So that was the major drawback in the computational model, that they have assumed the same properties which is measured at the periosteal surface. However, the endosteal surface is more permeable because the bone marrow, because the fluid which is going, the nutrients which is going to transfer into the bone marrows. So that is why the inner boundary is more permeable. Now this is the diagram with the mean deviations I have plotted. So as you can see here, the tibia is having higher permeability as compared to the femur bone, as well as at endocortical surface or endosteal surface is more permeable as compared to the periosteal surface. So then I've also compared the permeability between femur and tibia. So you can look at here at the endocortical surface, the tibia is having higher permeability as compared to the femur bone. Then at last we have also computed the Poisson's ratio. So the Poisson's ratio remains constant for femur as well as for tibia, and it also remains constant for the different anatomical locations. So the conclusion, so the finding of this study will be useful in accurate measurement of mechanical environment, regulating modeling and remodeling activities, which is essential to improve the biomechanical intervention to treat bone losses, means to develop the accurate physical exercise for sports biomechanics. And it is also observed that the endosteal surface is more permeable as compared to the periosteal surface in all the anatomical location, means anterior, posterior, medial, and lateral region. So the outcome of this study suggests that the poromechanical properties changes with location and with region, periosteal means with the regions also within the same bone tissue. So thank you. So if you have any doubt, these are the references. Thank you.
Any questions?
Thank you very much. It was a very nice and informative talk. And my question is, like you said that while working out, like the bone that you work, the bone density and the cross-section area increases and it gets probably stronger. By that you mean it gets stronger, right?
If you're going to apply the mechanical load, the cortical thickness of the bone is going to improve, means this cortical thickness means the bone mass is getting improved if you do the regular physical exercise. So if there will be a
loss will occur.
So you mean that like the bones that you are not using gets like their cross section was decreasing. So my question was that like in some people there it has been observed like for the spine. For the spine is like it's symmetry at the symmetry point and you have only one spine. You cannot and there is very less ways that you can work on your spine to make it strong. But the thing is like some people who don't work, their spine grows.
I just want to make a point over here. I'm talking about the bone remodeling and modeling processes. If you're talking about the spine, so every bone is having different mechanical properties or biomechanical properties. So according to the bone, we have to work. So right now I'm talking about the bone losses which occurs due to the bone disuse condition or disease conditions. So if you're talking about the disease condition in case of spinal cord injury or something, then we have to adopt the different protocols.
I was talking particularly about the spine growth. Like some people they have like with age there is like this cervical problem. This grows like some C1 or C0. It grows. So like initially you were saying that when you don't work on the bone, that it gets decreased inside and it its cross section decreases, while on the other hand I'm like it's like the case that I'm referring, not because of not working, it's growing in size.
Actually, the thing is like if you're talking about the osteoporosis, let's say we'll take a case of osteoporosis. So generally osteoporosis occurs in postmenopausal women. So as compared to women, women experiences osteoporosis at the early ages after the postmenopausal, whereas the men will having the higher bone mass and it take longest time. And and if you are going to apply the mechanical load means it doesn't mean always you are going to use the weight. If you're moving, if you're doing something, that's also a kind of physiological loading which is occurring upon the load. So a minute load can also improve the bone mass. But if it is a case of bedridden patient, so always you will be in the rest condition. You cannot move your body also. So that's why a physiotherapist is required, which is that person is moving your hand as well as fingers in order to increase the bone mass. And if you go for the space also, there the bone mass is getting reduced, and in space we cannot do the physical exercise. So in that case we have to apply the electromagnetic field, pulse electromagnetic field, because in space we know hypomagnetic field is there, so easily you can apply the pulse electromagnetic field, or you can use the anti-resorptive drugs, that is nothing but bisphosphonate, but longer uses will cause the osteoporosis. Thank you.
Any more questions? Okay, thank you, Dr. Abhishek. So Dr. Abhishek told us about the anatomy of our body and how we should take care of our body and think about it in a while. So now I would like to call paper ID 34. Please come on the stage.
Good evening, everybody. Now, this work is the inspiration by my father and my local MLA, Sri Vinod Narayan Jha. He said that अपने यहाँ हम इलेक्ट्रिफिकेशन के लिए क्या कर सकते हैं, क्योंकि जब मैं छोटा था तो हमने लालटेन में पढ़ाई की थी. हमारे यहाँ अभी इलेक्ट्रिफिकेशन आ गया है, लेकिन अभी उतनी ज़्यादा अमाउंट में नहीं आती है, बहुत कम आती है. Then he said that, ओके कुछ कीजिए सोलर से अगर हो सकता है तो हमारे पास फंड है एमएलए फंड हम कुछ कर सकते हैं देन this paper came into the existence. So now what I did the design and feasibility analysis for the on-grid solar photovoltaic power plant for the rural electrification of North Bihar state of India. Obviously this is my village and so I did for my village. This talk will follow the following sequence. First of all, I would like to determine the energy demand of the selected village and then design steps will follow. In this design steps we will see energy required from the PV module and then we will calculate the panel generation factor, what peak rating of the PV modules required and then number of PV modules required, then inverter size calculation and calculation of the PV module circuit, and after that we will also see the life cycle assessment of the plant, energy payback time of the plant, electricity production factor of the plant, capacity utilization factor, then life cycle conversion efficiency, and at last we will also see how much carbon credit we are earning through this renewable energy resources and greenhouse gas emission mitigation and carbon credit earned. And finally the financial assessment will be done, because without financial assessment we cannot move on this project. So as we already know that we have a very detrimental effect of the pollution on the human health. Not only on the human health but on the overall ecosystem is destroying because of the pollution, and air pollution is the major contributor in this area. And this is the photographs that has been directly obtained from the internet. So I would like to courtesy from the Wikipedia. So now, in this paper, North Bihar, there is a district called Madhubani, and my village is Pursaulia. I have selected this village for the solar PV power plant, and in this village there are 2,318 houses, and apart from the houses we have one Panchayat Bhavan, one meeting hall, one library, 4 primary and 1 middle school, and I would like to electrify all those bhavans and houses through the solar power plant. And I have seen that we need actually 2.5 megawatt plant size, and this electricity generated will be directly given to the nearest substation. Nearest substation is at Jayanagar city, and so I have obtained the solar data for the Jayanagar city. That Jayanagar city is nearly around 5 kilometers from my village, Pursaulia. So now, first of all, I would like to say that my village is divided into 4 tola, Purab, Paschim, Uttar, Dakhin, and each tola consists of some of the houses. In Purab tola it is 638 houses, Paschim is 459 houses, and Uttar tola is 893, and Dakhin is 410. Total number of houses is 2,318. And in each houses we have nearly, as you can see, 8 CFL, 4 fans, 1 TV, 2 mobile charger. Some of the households also have the refrigeration systems and washing machine, but that I haven't included because it is around less than 10% people have such type of amenities in the house. So now for the main buildings like Panchayat Bhavan, library, Panchayat Bhavan is very large. They have 4 tube lights, 12 fan, water cooler, 1 water cooler, and library have 16 tube lights, 20 fans. Primary schools and middle school cumulatively they are 5, and so the energy consumptions by the Panchayat Bhavan, library, primary and middle school multi-purpose hall has been also calculated, and it is around 112.4 kilowatt hour. Now, I would like to say you that Jayanagar, we have to obtain the solar radiation data of the Jayanagar city, and Jayanagar city longitude latitude is 26.590 north and 86.138 degree east, and this is the solar radiation kilowatt hour per meter square per day. In January it is 4.3, maximum you can obtain in May 7.3, quite high. In December it's very less, it's 4. Energy required, we can calculate that in energy demand multiply with the system compensation factor. Okay, so बहुत ज़्यादा फास्ट हो रहा है. So from this data you have to calculate the panel generation factor, and then this panel generation factor will give you the watt peak rating of the PV modules, and that watt peak rating is around 2.5 megawatt, and then number of PV, so we have selected the Tata Power Solar, the PV module obtained from the Tata Power Solar, and they have 330 watt peak value. That peak value have really reduced the size, area required by the solar power plant. And I would say that in 2008 I have found one paper, the case study, similar case study by Rahul Khatri, associate professor in MNIT Jaipur, and he would like to install the solar power plant in the hostel, Gargi hostel, and he was not quite optimistic with this case studies because of the high land cost in the Jaipur city and also the low peak rating of the PV module, and that time peak PV module rating was 220. And I phoned to the Rahul Khatri and he said that okay, now it may be possible and feasible. I'm not sure, but you can study. मैंने कहा सर आप थोड़े से पेसिमिस्टिक नहीं है इसके प्रति? उन्होंने कहा नहीं, ऐसा नहीं, उस समय जो अवेलेबल था मैंने कहा है ईमानदारी से, अगर आपको लगता है feasible है आपके गांव के लिए तो आप कीजिए, कोई दिक्कत नहीं. That Tata Power Solar, we have found a nearest supplier of this Tata Power Solar, and it was feasible. And then inverter sizing calculation, 3 inverter you need C1000 DC 1000 inverter that has been installed, and as you can see that in these calculations we have land requirement is only 7.2 acres. Okay, and also the in life cycle calculation electricity production factor is 5.203, and in other studies in India they have found very, very less, around 1.2 or 1.3. I would say it was marginal satisfactory. Then capacity utilization factor is 0.1770, but in other literature you will see that it is quite less because of the high rating of the PV module, and it was possible now. So I would like to say that the cost of the total plant will be 15 crore around. In 15 crore you can install 2.5 megawatt on-grid solar power plant efficiently. And I would like to say few things. Energy payback time is 5.765 years, and it is quite less. And before it was 8 years, 9 years. So no bank was able to finance this project. And this project is the part of DPR for the project funding through the bank. And total CO2 emission, what has been mitigated is 148,000 tons of CO2 you are mitigating. And if you will trade all the CO2, अगर आप केवल CO2 सेल करते हैं तो आपको इससे लगभग 20 करोड़ की आमदनी होती है. आप पूरे फ्री में पूरे गांव को इलेक्ट्रिसिटी दे सकते हैं. बट नो, if you are selling the total carbon credit, then what will happen? Someone is producing the same carbon, same pollution, so there is no advantage for the earth, okay, as a system. So what you can do 15 करोड़ की लागत के साथ अगर हम कैलकुलेशन करते हैं, इनिशियल कॉस्ट, ऑपरेटिंग कॉस्ट, रिप्लेसमेंट कॉस्ट, नेट साल्वेज वैल्यू, नेट प्रेजेंट वैल्यू, कैपिटल रिकवरी फैक्टर, तो एनुअलाइज्ड यूनिट कॉस्ट ऑफ इलेक्ट्रिसिटी 8 रुपीज़ के आसपास आता है, मैक्सिमम 10 रुपीज़, एंड इट मे बी लिटिल बिट हायर फॉर द रूरल एरिया. बट इफ़ यू विल सेल 40 to 50% कार्बन क्रेडिट अगर आप उसको सेल करते हैं इंटरनेशनल मार्केट में, देन कॉस्ट विल बी रिड्यूस्ड 5 to 6 रुपीज़ पर यूनिट, और गांव के लोग मेरे ख्याल से दे सकते हैं इतना. सो दिस इज द कंक्लूजन दैट यस, now we can install solar PV plant for the rural area, provided land should be very, very cheap. And as you can see that in my village, land is really cheap, 150 rupees per square feet, and 7.2 acre is required. 47 लाख रुपए में आपका लैंड हो जाता है. सेम जयपुर या न्यू दिल्ली की बात करेंगे तो कॉस्ट बहुत ज़्यादा हाई होगा. 2.5 मेगावाट इंस्टॉलेशन फॉर दिल्ली, इट विल बी रियली हाई. सो वी हैव टू सी द ऑप्टिमाइजेशन. क्या रूरल इलेक्ट्रिफिकेशन पॉसिबल है? मैंने सबसे पहले AHEC IIT रुड़की के पास, IIT रुड़की में AHEC है, डिपार्टमेंट अल्टरनेट हाइड्रो एनर्जी सेंटर. नाउ इट इज़ ए न्यू रिन्यूएबल एनर्जी सेंटर. And I talked to them that, sir, solar PV plant for rural electrification कैसा है? अरे मत जाओ, 18% तो ऑन पेपर है इफ़िशियंसी, आपको मिलेगा 10%, 12%, कुछ नहीं है. तो मैंने इस प्रोजेक्ट को छोड़ दिया. फिर उसके बाद पिताजी का फ़ोन आया, क्यों बेटा कुछ किए? मैंने कहा नहीं, प्रोफेसर बता रहे हैं फिजिबल ही नहीं है. मैंने कहा फिर मेरे पिताजी ने कहा तुम तो साइंटिस्ट हो, साइंटिस्ट का क्या काम होता है, पहले खुद करके देखे, खुद कल चल के देखो, फिसल जाओगे तो हम हैं ना, तुम चल के देखे. मैंने कहा नहीं, तो चलो करो, फिजिबिलिटी एनालिसिस तो करो कम से कम. फिर मेरा आर्गूमेंट था कि हम तो मतलब फोटोवोल्टिक सेल बनाने में भी तो हम कार्बन प्रोड्यूस कर रहे हैं, पॉल्यूशन एमिट कर रहे हैं. तो फिर उन्होंने कहा कि हम कैसे भी पॉल्यूशन तो हम इमिट कर ही रहे हैं, फोटोवोल्टिक सेल बनाने में, बैटरी बनाने में, इन्वर्टर बनाने में. पिताजी ने कहा पहले देख तो लो, मिटिगेशन कितना कर पा रहे हो, नहीं कर पा रहे हो, तब ना बात करोगे. तुम्हारी क्या फाइंडिंग्स है एज ए साइंटिस्ट? तो फिर मैंने इसको किया, और नाउ आई एम हैप्पी दैट इट इज़ इन प्रोग्रेस. And in few months, I will see 2.5 megawatt solar PV plant working. सबसे बड़ा चैलेंजिंग टास्क था कि हमारा जो गांव है वो बाढ़ का इलाका. लैंड आप कैसे, साइट कैसे फाइंड आउट करेंगे जहां पर पानी ना पहुंचे? नहीं तो पता लगा पूरा का पूरा सिस्टम ही नीचे गया. तो वो थोड़ा चैलेंजिंग टास्क था. इसीलिए गांव से हट के जयनगर में सोचा था कि गांव में ही सबको इलेक्ट्रिसिटी, लेकिन नहीं, ऑन ग्रिड करना. पहले ऑफ ग्रिड सोच रहे थे कि ऑफ ग्रिड ऑन ग्रिड दोनों मोड में चले, लेकिन नहीं चला. तो सो दिस इज द कंक्लूजन दैट इफ यू विल सेल 40% or 50% ऑफ द अर्न कार्बन क्रेडिट, देन इट इज़ फिजिबल 5 to 6 रुपीज़ पर यूनिट. ऑफ कोर्स इट इज़ लिटिल बिट हायर अगर आप सेल नहीं करते हैं कार्बन क्रेडिट, 8 रुपीज़ to 10 रुपीज़, बट इट्स ओके, नो प्रॉब्लम. So, thank you very much, my father, to inspire me to do this analysis. and my MLA Sri Vinod Narayan Jha for taking this initiative. Thank you very much.
Thank you so much, sir. Any questions from the audience?
Hello, sir. I work in BHEL in the solar energy department in Gurgaon, Solar Energy Research Center. And it's very good to see your determination to lighten your village. How good is the grid in your village? Because, you know, these estimations have not accounted for the, you know, grid instability.
ग्रिड इंस्टेबल नहीं, ग्रिड तो अच्छा है हमारे पास, मतलब 33/132 kV का है.
अच्छा, मतलब बिकॉज अगर आपके ग्रिड फेल हो जाएगा तो ये ऑन ग्रिड सिस्टम जो है वो ज़ीरो हो जाता है.
नहीं ग्रिड तो नहीं होगा.
अगर दिन के टाइम में आपका ग्रिड फेल हो गया तो सोलर जो प्रोड्यूस करेगा, बिकॉज इट विल नॉट बी स्टोर्ड इन एनी बैटरी, नथिंग इज देयर, सो आपका इलेक्ट्रिफिकेशन नहीं होगा. तो यू हैव टू कंसीडर दैट.
बात किया है इलेक्ट्रिसिटी डिपार्टमेंट से, बिहार नॉर्थ बिहार इलेक्ट्रिसिटी बोर्ड जो है उससे बात कर ली है.
ओके.
उन्होंने हमें कहा कि आप जयनगर सब ग्रिड में डालिए, मिलेगा आपको सही.
ओके,
क्योंकि इनिशियली हमारा प्रपोज था कि हम गांव को करें और ऑफ ग्रिड ऑन ग्रिड दोनों करें. उन्होंने कहा नहीं, आप सारा ग्रिड में डालिए, हम आपको पैसा देंगे. ऐसा.
थैंक यू.
Any other questions from the audience? Okay. Thank you so much, sir. This is a very grateful idea from sir. And this is a very big issue in most of the rural villages as of now, that they are suffering from lack of electricity. So it's a great initiative and idea. Thank you. So I would like to call the last paper ID of the day, the paper ID 486.
The Honorable Committee, professors, and all the participants of this international conference on future learning aspect in mechanical engineering, FLAME-2022. Myself, Mohammad Azad, and I'm from Mevat Engineering College. Basically, I'm an undergraduate student, and I'm here to present my paper titled Thermal Management Modeling of Photovoltaic System with Nanofluid for Semi-arid Climatic Condition. So, let's start with introduction. As we all aware about that, energy is the fundamental need for mankind today. It ensures better quality of life, and for our daily use, and uninterrupted energy has become a necessity for every human. And but we all are depend on non-renewable resources, and that degrade our environment and damaging our environment. So the only substitute of our renewable energy, the non-renewable resources, is that renewable energy, which is the human lifeline. And basically, renewable energy comes from many sources such as wind power, solar, biomass, water, geothermal. But that is PV, but the solar system is the only one that is take over the whole power against non-renewable resources. That is clean and green energy. A photovoltaic system is a device that convert the sun's radiation that are directly fall on the PV panel surface, and which is converted into usable electricity. But there is a problem with photovoltaic system, that is when the continuously solar radiation strike on the PV panel surface, then the temperature will also increase. That degrade the lifespan of our solar panel and also create thermal degradation on the solar cell that decrease the efficiency and lifespan and reduce the lifespan of the solar photovoltaic system. So cooling is very necessary for this. Basically, there are two type of technology in cooling: active cooling and passive cooling. Basically, active cooling are those cooling technologies which uses external source of power such as forced air, forced water circulation, etc. And passive cooling are those cooling which do not use external source of power, that use only natural convection way to extract the heat from the source or PV panel, and that extract and that reduce into that discharge in the environment by natural convection. So in our study, we use a nanofluid as a cooling medium to cool the PV panel temperature. Basically, nanofluid is a fluid that contains nanometer size particle called nanofluid. And these fluid are engineered colloidal suspension of the nanoparticle in a base fluid, and water is usually used as a base fluid. Basically, it has nanometer size metals like oxide, carbides, and carbon nanotubes by incorporation of nanofluid, base fluid to get a nanofluid. These are the literature. This is the literature review, which study I have already done in this related. Basically, the first author Young et al. Have developed a real climatic condition, develop a model on a photovoltaic system in real climatic condition, and uses a technique of water spraying in front of the solar photovoltaic surface, and that maintain a temperature up to 27 to 29 degree, which is critically reduced, and up to 14.37% efficiency they can get. The next author is Kesar et al. That is also develop a outdoor condition model in a test in a real climatic condition model, and that use a airflow force natural convection, and that also achieve a 35 degree, that also maintain a 35 degree temperature. And the next author is Chandrasekhar, that also develop a outdoor in real climatic condition test, and they use a special type of technique, cooling technique, that is cotton wick with water and aluminum oxide based water based nanofluid, and they achieve a good efficiency with a great reduction in temperature. That is, when temperature before cooling is 65, and after the using of these cooling medium like nanofluid, they can get a 45 degree or 54 degree temperature after cooling. Next slide is problem formulation. Basically, this model is in our problem. This model is developed by using answers by the incorporation of nanofluid to cool the PV panel surface. And basically, we will found that in that problem, the conventional PV temperature are different gradients. We will get a 72 degree, 77 and 82 degree centigrade at 850, 950 and 1,050 watt per centimeter square radiation. And after using the cooling medium, which is nanofluid, we will get a temperature at different intensities like 59.24, 63.03 and 66.82 degree centigrade. After that, we made our we'll discuss about research gap and implementation. Very limited study on the cooling of PV panel by the incorporation of the nanofluid for semi-arid climatic condition have been conducted. The use of the nanofluid in PV system for cooling purpose is critical because the different volume concentration of nanoparticle is used to achieve the thermal conductivity. And this is the model basically, which is designed in the special tool called Design Modeler. And this is the methodology we used in our study, that is CFD model we will develop. And in CFD model, first we will start, and then next step is post-processing the material, post-processing the modeling. That is, we will design in our special tool in ANSYS, that is design modeling. After that, we will move on meshing. Meshing is basically a iterative computational approaches that divide the partition into divide the partition into small region. And then after that we will move on boundary condition, and boundary condition after we select the appropriate boundary condition according to our study, and then we will move to post processing system, in which we will select different models like a 3D model or basically a solvent which is solve the numerical model in our software, and then we can get the result with the special tool called answers. And this is our result and discussion section in our study. Basically, this graph shows the panel average temperature distribution after cooling effect on the surface and nanofluid collector. Basically, first figure shows the average temperature on cooling effect on the surface of PV panel at constant flow rate, that is 0.0083 kg per meter square per second. Sorry. And the next figure will show the average nanofluid collector output temperature after the cooling. That is after that the minimum temperature we will get at radiation 850 watt per meter square, that is 57 degrees centigrade. That is the conclusion of our study. And so software 18.2 was used to model the PV thermal system in order to predict the thermal performance of PV system with and without cooling. And the PV surface and nanofluid outlet temperature were assessed using different heat fluxes. Ambient temperature and fluid inlet temperature 27 degree is used with constant heat flux, constant mass flow rate, that is 0.083 kg per second, by using aluminum oxide water-based nanofluid with 0.5% volume concentration of nanoparticles. It was observed that thermal conductivity of nanofluid is increased as the volume concentration of nanoparticles increased in the fluid. Finally, the use of nanofluid in the thermal regulation of PV system gives better performance when compared without cooling and improves the PV efficiency in an effective way. Thank you so much. That's the references which I used in our literature review. That's all about my book. Thank you so much.
Thank you so much. Any questions from the audience? Okay.
एक्चुअली ये आपने बनाया था या सिर्फ सिमुलेशन मतलब किया है इसका?
सर सिमुलेशन कराए थे एक्चुअली, और हमारा एक एक्चुअल में ऑनगोइंग है ये प्रोजेक्ट, तो इसे आफ्टर दैट वी विल ओनली शो इन कॉन्फ्रेंस इन द टेम्परेचर डिस्ट्रीब्यूशन एंड द यूज ऑफ नैनोफ्लूइड।
नहीं, इसका जब फिजिकली बनाया था, फिजिकली आपने फिजिकली नैनोफ्लूइड को फ्लो करा के और फिजिकली मेजर किया था?
सेटअप नहीं था इसका, अब बनाया तो वो एक्चुअल में इसे वैलिडेट नहीं कराया, इसीलिए हमने इसमें इस पेपर में।
तो ये जो नैनोफ्लूइड ये फ्लो किस में करेगा, मतलब कहाँ पे ये आप फ्लो कराएंगे उसको?
ये फ्लो कराएंगे एक्चुअली पैनल्स के साथ अटैच कराया हमने, जो ट्यूब्स के साथ इसे मतलब वाटर कलेक्टर इसमें लगाया है, इसमें नैनोफ्लूइड हमने फ्लो कराया है।
नहीं, ये कहाँ पे फ्लो करेगा, मतलब ग्लास में होगा, ये माइक्रो चैनल्स में कुछ चैनल्स होंगे, ये ग्लास में होगा ऊपर की तरफ या नीचे की तरफ? जो बैक साइड पे, बैक साइड में जहाँ पे आपके टेडलर, ये आपके टेडलर होती है, तो ये टेडलर के पीछे होगा? अच्छा, और ये मतलब फ्लो कैसे करेगा, ये हीट की वजह से? व्हाट विल बी द लाइक व्हाई विल इट फ्लो? ये चैनल्स में क्यों फ्लो करेगा, कैसे फ्लो करेगा? व्हाट विल ड्राइव दिस फ्लूइड, व्हाट विल ड्राइव दिस फ्लूइड टू फ्लो? दिस विल बी फोर्स बाय लाइक मोटर लगी होगी, या फिर ये थर्मल कैसे ये मूव करेगा फ्लूइड, क्यों मूव करेगा फ्लूइड? अच्छा, ओके, थैंक यू।
Thank you so much, sir. Those were some great ideas. So this is the end of this session, and there is an announcement. All the guests and presenters who are going to the gala dinner in the Lemon Tree are informed that the bus service will be available, and it will be from F2 Auditorium at 6:15 p.m. Thank you. At the last, I would like to invite Dr. Shyamal Saman sir to come on the stage and provide a thank you momentum to our session chair. Thank you so much, sir. Thank you, everyone.